Good evening and welcome to the Late Lab. I'm very glad you've joined me. Before we settle into tonight's subject, tell me where you're listening from. Perhaps you're tucked beneath the covers, stretched out on the sofa, travelling somewhere beneath the evening sky, or simply enjoying a few quiet minutes before sleep. Wherever this finds you, I hope the day is beginning to loosen its grip, and that you can make yourself comfortable for a little while. These calm journeys into science are only possible because people choose to return, so if you enjoy spending time here, a like and a subscription are always deeply appreciated. And if you've been with the Late Lab for a while already, thank you. Your support helps this small corner of the internet remain quietly illuminated. Tonight, we're going beneath the surface of almost everything we know. Beneath atoms, beneath particles, and even beneath what appears to be completely empty space, modern physics describes an invisible landscape of quantum fields. I'll do my best to explain it gently enough that you can relax, although discovering that empty space is not especially empty may not be the most reassuring thought to take to bed. Still, there are worse things to lose sleep over, so let's ease our way in. What are quantum fields? And could they really be the hidden reality beneath everything? Look around you for a moment, and the world appears to be made from objects. There may be a table nearby, steady and reassuring beneath whatever has been placed upon it. Your hand may be resting against a blanket, a chair, or the cool surface of a glass. The room contains air, though it is mostly invisible, and far beyond the walls a distant star may be pouring light across an enormous stretch of space. These things seem very different from one another. A table appears solid. Air seems almost empty. Light feels less like an object and more like something passing through the world. A star is so remote and immense that it hardly belongs in the same category as a human hand. Yet modern physics describes all of them using the same underlying idea. Beneath every visible object, every atom, every recognized particle, and every region that appears completely empty, there are quantum fields extending throughout the universe. This does not mean that familiar objects are illusions, or that the table beside you is secretly imaginary. It means that solidity, matter, and light are not built in quite the way human intuition first suggests. We often picture atoms as tiny solar systems and elementary particles as perfectly solid beads, each one moving through an otherwise empty background. That picture can be useful at first, but it is not the deepest description offered by modern physics. At the most fundamental level currently available to particle physics, nature is described through fields. A field is something that has a value, condition, or measurable property at every point in space and time. A weather map provides a familiar comparison. At every location on the map, the air may have a particular temperature, pressure, and wind direction. Together, those values form temperature fields, pressure fields, and wind fields. A physical field is not merely a map drawn by humans, however. It is part of the scientific description of nature itself. The electromagnetic field, for example, can possess different strengths and directions at different locations. Those conditions determine how electrically charged matter will behave. It is important not to imagine a field as an ordinary fluid quietly filling space. Water occupies a region, because water molecules are present there. A quantum field is not currently understood as being made from smaller material pieces flowing through an underlying emptiness. As far as established quantum field theory is concerned, the field is itself part of the basic description. There is an electron field throughout the universe. There is also an electromagnetic field, along with several quark fields, neutrino fields, gluon fields, and the Higgs field. These fields are not usually visible, but their excitations and interactions produce the matter and radiation that can be observed. An electron is therefore not described as a tiny object existing independently of the electron field. It is understood as a localized quantum excitation of that field. A photon is an excitation of the electromagnetic field. The word excitation simply means that the field is in a state containing a particular amount of energy, momentum, and other physical properties. A calm lake can support a wave, but the wave is not a separate substance added to the lake. It is a pattern carried by the water. The comparison is helpful, although it has limits. A quantum field is not known to rest on a deeper material medium, and a quantum particle is not merely a classical ripple with a definite shape and path. Quantum excitations behave according to probability amplitudes, uncertainty, and superposition. They can spread through space like waves and then exchange energy in sharply localized events. This is one reason particles can appear so puzzling. In one experiment, light produces an interference pattern associated with wave behavior. In another, it arrives at a detector in individual packets called photons. Quantum field theory does not force nature to choose between being made of waves or particles in the classical sense. Instead, both kinds of behavior emerge from quantum fields. Quantum field theory is the framework created by bringing together three major ideas. The first is the classical concept of fields, developed most powerfully in 19th century electromagnetism. The second is quantum mechanics, which describes energy, matter, and measurement at atomic and subatomic scales. The third is special relativity, Albert Einstein's theory explaining how space, time, energy, and momentum behave when motion approaches the speed of light. Each of these ingredients is essential. Classical field theory alone cannot account for the discrete quantum behavior observed in atoms and radiation. Ordinary quantum mechanics can describe systems with fixed numbers of particles, but special relativity permits particles to be created and destroyed whenever energy is transformed. Quantum field theory can describe both processes because particles are temporary excitations of fields rather than permanent pieces that must always exist. Its most successful application is the Standard Model of particle physics. The Standard Model describes the known elementary matter fields and three of the four recognized fundamental interactions. It includes electromagnetism, the weak interaction, and the strong interaction. These govern processes ranging from chemistry and radioactive decay to the binding of quarks inside protons. Gravity remains outside this complete quantum description. Einstein's general theory of relativity describes gravity with remarkable accuracy as the curvature of space-time, but combining gravity fully with quantum field theory remains one of the great unfinished problems in physics. For that reason, quantum fields may be described as the invisible reality beneath everything, but not as the final explanation of absolutely everything. The phrase refers to the extraordinary range of phenomena explained by the field framework, not to a claim that science has reached the final page of nature's instruction manual. Quantum fields cannot be seen directly in the way a chair or a planet can be seen. Their existence is inferred from effects that can be measured with extraordinary precision. Electrons leave signals in detectors. Photons transfer energy to atoms. Quantum fields predict particle collisions, atomic spectra, magnetic behavior, and radioactive decay. The invisible becomes known through what it causes. That distinction matters. Human senses reveal only a narrow selection of physical reality. Eyes respond to a small band of electromagnetic radiation. Touch responds to electrical interactions between atoms. Solidity itself emerges from electromagnetic forces and quantum principles rather than from tiny surfaces pressing together like polished stones. Beneath the familiar world lies something less solid, more dynamic and far stranger than appearances suggest. There are fields extending through space. Their excitations appear as particles. Their couplings create forces. Their symmetries determine which transformations are possible. Even their lowest energy state, the quantum vacuum, is not simply an absence of activity. From these invisible structures come atoms, light, chemistry, stars, and living bodies. The quiet room around you may look still, but at the deepest level we can currently describe, reality is never merely sitting there. It is being continually expressed through fields. Long before physicists began speaking about quantum fields, Nature was usually imagined as a collection of separate objects moving through empty space. A planet travelled around the sun, a stone fell towards the ground. Two pieces of matter could collide, rebound, pull apart, or remain at rest. The universe seemed to consist of things, along with the forces acting between them. This mechanical picture became extraordinarily powerful during the scientific revolution. Motion could be described through mathematics, and complicated events could be understood as the combined behaviour of simpler parts. Instead of explaining the world through hidden intentions or unseen purposes, physicists increasingly searched for precise laws connecting cause and effect. Isaac Newton transformed that approach. His laws of motion provided a general framework for describing how objects accelerate when forces act upon them. His law of universal gravitation then connected events on Earth with events in the heavens. The same gravitational attraction that caused an apple to fall could also explain the orbit of the Moon and the motion of planets around the Sun. Newtonian gravity described the strength of attraction between two masses with astonishing accuracy. The force became weaker with the square of the distance between them, meaning that doubling the separation reduced the attraction to 1/4 of its former strength. This simple relationship explained a remarkable range of observations. Yet beneath its success lay an uncomfortable question. How did one object reach across empty space and pull upon another? Newton's equations stated how strong the attraction would be, but they did not provide a physical mechanism travelling between the bodies. The Sun influenced Earth across roughly 150 million kilometres of space. Earth influenced the Moon across nearly 400,000 kilometres. In the mathematical description, each mass seemed to know where the others were and respond accordingly. Newton himself was cautious about claiming that gravity acted through empty space without any mediating process. The calculations worked beautifully, but the underlying picture remained unsettled. For a long time, this was not enough to stop physics progressing. A theory can make excellent predictions even while leaving deeper questions unanswered. Nature is under no obligation to make every successful equation immediately intuitive, which is fortunate because physicists would otherwise have far fewer equations. The field concept offered a different way to think about influence. Rather than saying that one object directly reaches across space to affect another, a field assigns physical properties to the region surrounding the object. A massive body can be described as producing a gravitational field throughout nearby space. At each location, that field has a strength and direction. Another mass placed within the region responds to the field present at its own position. This does not necessarily solve every philosophical question about gravity, but it changes the structure of the explanation. Space is no longer treated as a completely empty gap separating distant bodies. The region between them becomes physically significant. This shift became especially important in the study of electricity and magnetism. During the 19th century, Michael Faraday carried out a long series of experiments involving magnets, wires, electric currents, and changing magnetic environments. Faraday had relatively little formal mathematical training compared with some of his contemporaries, but he possessed an exceptional physical intuition. He visualized electric and magnetic influence using lines of force. Iron filings scattered around a magnet arranged themselves into curved patterns. These visible shapes do not reveal literal threads stretching through space, but they help represent the direction of the magnetic field at different locations. For Faraday, the region around a magnet was not merely an empty stage. It possessed structure. The magnetic influence existed throughout the surrounding space, and changes in that influence could produce measurable effects elsewhere. Faraday's experiments on electromagnetic induction showed that a changing magnetic environment can generate an electric current. A magnet moved through a coil of wire can produce electrical motion within the conductor. Likewise, a changing electric current can produce a changing magnetic field. Electricity and magnetism were not isolated phenomena. They were deeply connected. The field idea gave this connection a natural language. Electric charges produced electric fields. Moving charges and electric currents produced magnetic fields. Changing fields could generate one another. James Clerk Maxwell later transformed Faraday's physical insights into a unified mathematical theory. During the 19th century, Maxwell developed a set of equations describing electric and magnetic fields and the way they evolve. These equations showed that a changing electric field produces a magnetic field, while a changing magnetic field produces an electric field. The remarkable consequence was that electric and magnetic disturbances could sustain one another. A changing electric field could create a magnetic field. That changing magnetic field could then create another electric field slightly farther away. The linked disturbance would propagate through space as a wave. When Maxwell calculated the speed of these electromagnetic waves, the result matched the measured speed of light. Visible light was therefore not a completely separate phenomenon. It was an electromagnetic wave. This was one of the great unifications in physics. Electricity, magnetism, and optics became different expressions of the same underlying field system. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays would eventually be understood as electromagnetic waves, differing mainly in wavelength and frequency. Classical fields had become more than convenient bookkeeping devices. They could carry energy from one location to another. Sunlight transports energy across space and warms the surface of Earth. A radio transmitter sends electromagnetic energy outward through its surrounding field. Fields can also carry momentum, allowing light to exert a tiny pressure on matter. None of this requires the field to behave like an ordinary collection of material particles. A classical electromagnetic wave can spread through vacuum. It has no need for air, water, or another familiar medium. It consists of changing electric and magnetic fields travelling together through space. In classical physics, those fields vary continuously. A wave can be made stronger or weaker by any chosen amount. Its energy can, in principle, be divided into endlessly smaller portions. There is no minimum packet required by the classical theory. That assumption seems perfectly natural when considering ocean waves or vibrations on a string. A ripple can be gentle, then gentler still. Nothing in the classical field description prevents the energy from being reduced without limit. Quantum physics would eventually reveal that this picture was incomplete. The electromagnetic field can exchange energy in discrete quanta called photons. Other fields also possess quantized excitations. What classical physics treated as a smoothly varying field would have to be reinterpreted through quantum principles. Still, the classical field idea was the essential first step. Faraday and Maxwell changed space from an empty background into a place containing physical conditions capable of storing energy, carrying momentum and transmitting influence. Once fields had been accepted as genuine parts of nature, a more radical possibility became imaginable. Perhaps particles were not entirely separate objects moving through fields. Perhaps the particles themselves were expressions of fields. The classical field picture had transformed physics. Electricity, magnetism, and light could now be understood as different expressions of one continuous electromagnetic field. Energy could move through space in waves, and matter could respond to those waves in predictable ways. For a while, this appeared to be a remarkably complete account. Then physicists began looking more closely at the relationship between light, heat, and matter. The results were deeply troubling. One of the central problems involved blackbody radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation falling upon it, and, when heated, emits a characteristic spectrum of radiation determined by its temperature. Real objects are not perfect blackbodies, but many hot bodies behave closely enough to make the concept useful. A glowing piece of metal, the surface of a star, and the warm interior of a furnace all emit electromagnetic radiation across a range of wavelengths. At lower temperatures, most of that radiation lies in the infrared and cannot be seen by human eyes. As temperature rises, the emitted spectrum shifts. A heated object may begin to glow dull red, then orange, then yellow, and eventually appear white as more visible wavelengths become strongly represented. By the end of the 19th century, experimental measurements of blackbody radiation were becoming increasingly precise. Classical physics could describe parts of the spectrum reasonably well, but when the same assumptions were extended to shorter wavelengths, the mathematics produced an absurd result. The theory predicted that a hot object should emit more and more energy at increasingly high frequencies. In the ultraviolet region and beyond, the total predicted energy rose without limit. This became known as the ultraviolet catastrophe. No real furnace released infinite energy. Laboratories remained pleasantly intact. The failure lay in the theory. The problem emerged because classical physics allowed the electromagnetic field to exchange energy continuously. Every possible mode of vibration could contain any amount of energy, however small, and the vast number of high-frequency modes collectively produced the runaway prediction. In 1900, Max Planck found a mathematical solution. Planck proposed that matter did not exchange energy with electromagnetic radiation in arbitrary continuous amounts. Instead, energy was emitted or absorbed in discrete packets. The size of each packet depended on the frequency of the radiation. In clear English, the relationship states that the energy of one quantum equals Planck's constant multiplied by the frequency. Planck's constant is an extremely small fundamental quantity. Its smallness explains why energy usually appears continuous at everyday scales. A lamp, a fire, or a warm human body emits an immense number of quanta, so the individual steps are far too fine to notice directly. At atomic scales, however, the steps matter. Higher frequency radiation is exchanged in larger energy packets. Lower frequency radiation is exchanged in smaller ones. This restriction prevented arbitrarily tiny amounts of energy from being distributed among endlessly many high-frequency modes, resolving the ultraviolet catastrophe. Planck initially treated quantization cautiously. It was a successful rule, but its deeper physical meaning was not yet clear. Albert Einstein pushed the idea further. In 1905, Einstein examined the photoelectric effect, in which light striking certain materials causes electrons to be released. Classical wave theory seemed to suggest that brighter light should always deliver more energy to the electrons. If enough light accumulated, even low-frequency radiation ought eventually to free them. Experiments did not behave that way. Below a certain threshold frequency, no electrons were emitted regardless of how intense the light became. Above the threshold, electrons could be released almost immediately. Increasing the frequency increased the maximum energy of the emitted electrons, while increasing the intensity mainly increased how many electrons were released. Einstein explained this by proposing that light itself transfers energy in individual quanta. Each quantum carries an amount of energy determined by its frequency. If one quantum does not contain enough energy to free an electron from the material, adding more low-energy quanta does not help that individual interaction. It merely provides more insufficient packets. Higher frequency light carries more energy per quantum and can therefore cross the threshold. These light quanta were later called photons. The photoelectric effect revealed that intensity and frequency are not interchangeable. Greater intensity means more photons arriving over a given time. Greater frequency means more energy carried by each photon. Light still displayed interference and diffraction, unmistakable signs of wave behavior. Yet it also exchanged energy in discrete events. Nature had become difficult to fit into either the classical category of wave or the classical category of particle. Atoms soon deepened the mystery. Niels Bohr proposed an early quantum model of the atom in 1913. In Bohr's picture, electrons could occupy only certain allowed energy levels around the nucleus. They could move between those levels by absorbing or emitting specific amounts of energy. This helped explain why atoms produce discrete spectral lines rather than every possible color. The Bohr model was not a complete modern description of the atom. Electrons are not tiny planets travelling along neat circular tracks. Still, the model captured something essential. Atomic energy is quantized. The continuous machinery of classical physics could not explain why only particular energies were allowed. Louis de Broglie then proposed that matter itself possessed wave properties. If light, long regarded as a wave, could display particle-like behaviour, perhaps particles such as electrons could also display wave-like behaviour. De Broglie connected a particle's momentum with an associated wavelength. This proposal was later supported by experiments showing electron diffraction. Erwin Schrödinger developed wave mechanics, describing quantum systems through a wave function that evolves according to the Schrödinger equation. The wave function does not behave like an ordinary water wave or sound wave. It encodes quantum amplitudes connected to the probabilities of possible measurement outcomes. At almost the same time, Werner Heisenberg developed matrix mechanics, a mathematically different but physically equivalent formulation of quantum theory. Heisenberg also introduced the uncertainty principle. The uncertainty principle states that certain pairs of quantities, most famously position and momentum, cannot both possess arbitrarily precise values within the same quantum state. This is not merely a complaint about clumsy instruments. It is not that an electron has one perfectly definite position and momentum, while the laboratory simply fails to discover them. Quantum theory places a structural limit on how sharply both properties can be defined together. A state concentrated very narrowly in position must involve a wider range of possible momenta. A state with very sharply defined momentum must be spread more broadly through space. Quantum mechanics proved extraordinarily successful. It explained atomic spectra, chemical bonding, the structure of materials, and many properties of radiation. It described probabilities with remarkable accuracy and revealed that the microscopic world was governed by principles unlike those of ordinary classical objects. Yet the earliest forms of quantum mechanics usually described a fixed number of particles. That was acceptable for many atomic problems. One could study a particular number of electrons interacting with a nucleus and calculate how their quantum state evolved. Special relativity made this limitation impossible to ignore. Relativity allows energy to be transformed into massive particles. Particles can also annihilate, converting their energy into other excitations such as photons. In high-energy processes, the number and type of particles present before an interaction may differ from those present afterwards. A theory built around a permanently fixed collection of particles could not describe such transformations naturally. The solution was to apply quantum principles to the fields themselves. A quantum field could gain an excitation, producing what observers identify as a particle. It could lose an excitation, corresponding to annihilation. Several excitations could interact and emerge as different excitations, while energy, momentum, charge, and other conserved properties remained balanced. The quantum revolution had begun by changing the meaning of energy. It would continue by changing the meaning of a particle. Quantum mechanics had transformed the understanding of atoms, light, and energy. Yet another revolution was already forcing physics to change again. In 1905, Albert Einstein introduced the special theory of relativity. The theory rests on two central principles. The first is that the laws of physics are the same for all observers moving at constant velocity relative to one another. Such observers are called inertial observers. None of them occupies a uniquely privileged state of rest. The second principle is that the speed of light in vacuum is measured to be the same by every inertial observer, regardless of the motion of the light source or the observer. This is profoundly unlike everyday motion. If someone walks forward inside a moving train, a person standing beside the tracks measures the walker's speed as the motion of the train combined with the walking speed. Light does not follow that familiar rule. Every inertial observer measures light in vacuum travelling at approximately 300,000 kilometers per second. To preserve this constant speed, measurements of space and time must depend on motion. Moving clocks run slowly relative to stationary ones. Distances along the direction of motion become contracted. Events that are simultaneous for one observer may not be simultaneous for another. These effects are usually tiny at ordinary speeds. They become important only when motion approaches the speed of light, which is considerate of nature, since daily life is complicated enough already. The mathematician Hermann Minkowski later expressed special relativity geometrically. Space and time are not completely separate ingredients. They are joined into a four-dimensional structure called space-time. An event is defined not only by where it occurs, but also by when it occurs. Different observers may divide space-time into space and time in different ways, yet they agree on deeper space-time relationships. This geometric structure places strict limits on how physical influences can travel. No object carrying information can be accelerated through the speed of light in vacuum, and causes must remain connected to their possible effects through the structure of space-time. Relativity also changed the relationship between energy, momentum, and mass. The most famous expression associated with the theory states that energy equals mass multiplied by the speed of light multiplied by the speed of light. This is commonly called mass-energy equivalence. It does not mean that matter is simply a box filled with a substance called energy. Energy is a measurable property of a physical system, not a material ingredient poured into it. Mass contributes to the total energy of an object, even when the object is at rest, while motion and interactions contribute additional energy. Because the speed of light squared is an enormous conversion factor, even a small amount of mass corresponds to a very large amount of rest energy. The relationship also works in the opposite direction. If enough energy is concentrated under the correct conditions, massive particles can be created. A high-energy photon passing near an atomic nucleus can produce an electron and a positron, provided there is enough energy and the surrounding interaction allows momentum to be conserved. An electron and a positron can also annihilate, producing photons. Particles are therefore not permanent objects whose number must remain fixed. Their properties are constrained by conservation laws, but particles themselves may appear, disappear, or transform. This created a serious problem for ordinary non-relativistic quantum mechanics. The Schrödinger equation works extremely well when particles move much more slowly than light and when the number of particles can be treated as fixed. It remains essential for atomic physics, chemistry, and many areas of condensed matter science. But it is not fully compatible with special relativity. At sufficiently high energies, collisions can create new particles. Existing particles can decay into different ones. A theory that begins by assuming a fixed number of permanent objects cannot naturally describe these reactions. Physicists therefore searched for a relativistic quantum equation. One of the most important advances came from Paul Dirac. In 1928, Dirac introduced an equation describing electrons in a way that respected both quantum mechanics and special relativity. The Dirac equation was remarkable for several reasons. It naturally incorporated electron spin. Spin is an intrinsic quantum property related to angular momentum, although it should not be pictured as a tiny sphere literally rotating around its axis. The equation also reproduced the correct magnetic behavior of the electron with striking success, yet it contained solutions with an unexpected form. These states were eventually interpreted as describing a particle with the same mass as the electron, but the opposite electric charge. This was the positron, the electron's antiparticle. At first, the predictions seemed deeply strange. No matter did not appear to contain positively charged electrons wandering around in abundance. Then, in 1932, Carl Anderson studied tracks left by cosmic ray particles in a cloud chamber. A cloud chamber contains supersaturated vapor in which charged particles produce trails of tiny droplets. When placed in a magnetic field, the curvature of a track reveals the sign of the particle's electric charge and gives information about its momentum. Anderson observed a particle curving in the direction expected for a positive charge while behaving like an electron in mass. The positron had been found. Antimatter was no longer merely an unusual feature of an equation. It was part of the physical world. The discovery strengthened the need for a theory in which creation and annihilation were built into the foundations. In quantum field theory, an electron is an excitation of the electron field. A positron is the corresponding antiparticle excitation. When sufficient energy is available, the field can enter a state containing an electron and a positron. When they annihilate, those excitations disappear and the energy is transferred into other fields, commonly producing photons. Nothing is created without rules, and nothing simply vanishes. Energy and momentum are conserved. Electric charge is conserved. Angular momentum and other relevant quantum properties must also remain balanced. Creation and annihilation are lawful transformations within a network of interacting fields. This is why quantum field theory treats fields as primary. A fixed collection of particles cannot remain fixed in a relativistic universe. Fields, however, can support different numbers of excitations at different times. They provide a continuous framework within which particles can be produced, absorbed, and transformed. Relativity also requires locality. Locality means that physical interactions occur through neighboring regions of space-time. A disturbance can propagate outward, but it cannot be used to send a controllable influence instantaneously across an arbitrary distance. Quantum theory does contain correlations that can extend across space, particularly through entanglement. Yet these correlations do not allow usable information to travel faster than light. Relativistic quantum fields are constructed so that operations performed in regions separated beyond possible light-speed communication cannot be used to create direct controllable effects between them. Special relativity therefore did much more than provide corrections for unusually fast particles. It changed what a consistent quantum theory had to describe. The fundamental framework could no longer be a set of permanent miniature objects moving through space. It had to include entities spread throughout space-time, capable of supporting changing numbers of excitations, while preserving causality and conservation laws. Quantum fields were not simply a more elegant option. Relativity had made them necessary. A classical field can be imagined as a physical condition spread across space. At every location, the field has some value. The temperature in a room can be described this way. So can the strength and direction of an electric field, a magnetic field, or a gravitational field. A quantum field begins with the same broad idea, but it is governed by quantum principles. Instead of possessing one completely definite classical configuration at every moment, a quantum field is described by a quantum state. That state contains amplitudes for different possible configurations of the field. These amplitudes are not ordinary probabilities by themselves. They can combine, reinforce one another, and cancel one another through interference. Only when the theory is connected to a particular measurement do the amplitudes determine the probabilities of the possible outcomes. This is one of the first reasons quantum fields feel unfamiliar. A classical field may have a definite strength at every location, even when nobody has measured it. A quantum field can occupy a state in which several different field configurations contribute to the description at once. The field is not simply hiding one ordinary arrangement that physicists have failed to uncover. Quantum theory describes the range of possibilities as part of the physical state itself. Every recognized elementary particle is associated with a corresponding quantum field. There is an electron field extending throughout space. There are several quark fields, including the up quark field and the down quark field. There are neutrino fields. The electromagnetic field is associated with photons, while gluon fields are involved in the strong interaction. The Higgs field also extends throughout the universe and plays a central role in the masses of several elementary particles. Saying that the electron field exists everywhere does not mean that an electron is present and detectable at every point. A field can exist in a state containing no particle excitations at all. It can also occupy a state containing one electron, several electrons, or a much more complicated arrangement of particles and interactions. The field and the particles are therefore not the same thing. The field is the underlying quantum entity. A particle is one possible excitation of that field. It is tempting to picture the field as a substance filling a container, rather like air filling a room or water filling an ocean. That image can be useful for a few moments, but it quickly becomes misleading. Air is made from molecules, water is made from molecules. Their behavior emerges from smaller material constituents moving through space. A quantum field is not presently known to be made from a deeper collection of tiny objects. Within quantum field theory, the field is treated as fundamental. There is no confirmed microscopic fabric underneath the electron field from which electrons are woven. There is no known material sheet carrying the electromagnetic field in the way a rubber membrane carries ripples. A continuous surface can still provide a gentle analogy. Imagine a wide, flexible sheet capable of supporting many patterns. A small disturbance might produce one localized pulse. A broader disturbance might spread across the surface. Several patterns could overlap and interfere. The sheet itself would remain present even when it appeared calm. A quantum field behaves similarly in the limited sense that it can support different excitations and patterns. But the analogy must stop there. A physical sheet is made from atoms, occupies ordinary space, and can vibrate because of its material structure. A quantum field has no known supporting sheet beneath it. It is not vibrating inside space in quite the same way that fabric vibrates inside a room. The field is part of the physical description of space and time. Mathematically, a field can be broken into modes. A mode is a particular pattern of variation with a characteristic wavelength and frequency. On a stretched string, one mode might describe a broad vibration involving the entire string. Another might contain more tightly spaced peaks and troughs. A classical field can be analysed in a similar way. Complicated waves can be built by combining many simple modes. Quantum field theory takes each mode and treats it in a manner resembling a quantum oscillator. A classical oscillator can possess any amount of energy. Its motion can be made smoothly weaker or stronger. A quantum oscillator has discrete allowed energy levels. This process is called quantization. The energy stored in a field mode does not change through every imaginable value without restriction. It changes in steps. For the electromagnetic field, one quantum of excitation is a photon. Adding one photon means placing one discrete unit of excitation into the relevant electromagnetic mode. Adding another photon raises the excitation by another unit. The electron field is more complicated because electrons belong to a different category of particles, but the central idea remains. One suitable excitation of the electron field is identified as one electron. This language may sound as though particles are merely vague disturbances with no individuality. Yet the field description explains one of the most remarkable facts in nature. Every electron is identical to every other electron. All electrons possess the same electric charge, the same mass and the same intrinsic spin. No experiment has ever revealed one electron to be slightly heavier, slightly more charged, or subtly better made than another. In a miniature object picture, this perfect sameness seems almost miraculous. Nature would need to manufacture an enormous number of separate particles with absolute precision. Quantum field theory provides a deeper explanation. Electrons are identical because they are excitations of the same electron field. They are not separate products constructed according to a shared design. They are repeated manifestations of one underlying field. The same principle applies to photons, quarks, and the other elementary particles. A photon produced inside a distant star and a photon produced in a laboratory are excitations of the same electromagnetic field. Quantum fields fall into two broad families. Bosonic fields produce bosons, including photons, gluons, the weak force bosons, and the Higgs boson. Fermionic fields produce fermions, including electrons, quarks, and neutrinos. The difference is connected to a quantum property called spin, and to the statistical rules governing groups of identical particles. Bosons can occupy the same quantum state in large numbers. Fermions are restricted by the Pauli exclusion principle, which prevents identical fermions from occupying precisely the same quantum state. These contrasting behaviors help explain why photons can gather into intense coherent beams of laser light, while electrons arrange themselves into the layered structure of atoms and matter. A quantum field state can also be spread across several possible arrangements. A state may contain an excitation that is not perfectly localized at one point. It may involve different possible positions, momenta or particle numbers. Interactions can even produce superpositions involving different combinations of excitations. When a measurement occurs, the possible outcomes are governed by the quantum amplitudes contained in the state. This does not mean that reality is arbitrary. Quantum field theory makes precise statistical predictions, often confirmed to extraordinary accuracy. What it does mean is that the theory does not generally assign one classical history to every particle before measurement. The word particle remains extremely useful. Detectors record localized events. An atom absorbs a definite amount of energy. A semiconductor produces a small electrical signal. A particle collider records momentum deposited in a particular region of a detector. These events appear particle-like because energy, momentum and charge are exchanged in discrete amounts. Yet the quantum state responsible for the event may have been spread across a much larger region before the interaction occurred. A photon can travel through an interferometer in a state involving more than one possible path, then produce one localized detection signal. An electron can be described by a spatially extended quantum amplitude, yet leave a distinct mark when it interacts with matter. Quantum field theory therefore preserves the usefulness of particles without treating them as tiny classical beads. Particles are the discrete detectable excitations of fields whose states can also display wave-like extension, interference and uncertainty. There is strong experimental support for this framework. Quantum field theories predict atomic transitions, scattering probabilities, particle decays, magnetic properties, and collider outcomes with exceptional precision. That success does not automatically settle every philosophical question. Some physicists speak as though quantum fields are the true substances of reality. Others are more cautious and treat quantum field theory as an extraordinarily successful mathematical framework without claiming that its equations reveal the final furniture of existence. The experiments establish that quantum fields describe particle behavior remarkably well. Whether fields are literally the only things that exist, or whether they emerge from something deeper, remains open. For now, the most reliable statement is also the most quietly astonishing. What appears to us as a world of separate particles can be described as a world of fields, extending everywhere, supporting discrete excitations and shaping every measurable interaction. Calling a particle a ripple in a quantum field is useful, but is only the beginning of the explanation. A particle is not simply a tiny classical wave crest travelling neatly from one place to another. An ocean wave has a visible peak, a definite shape and a material medium beneath it. A quantum particle behaves differently. It is a quantist excitation of a field, carrying specific physical properties such as energy, momentum, electric charge and spin. These properties are not decorative labels added afterwards. They determine how the excitation moves, what it can interact with, and how it may transform. An electron carries one fixed unit of negative electric charge. Every electron also possesses the same mass and the same intrinsic spin. A photon carries energy and momentum but has no electric charge and no rest mass. Different particle types correspond to excitations of different quantum fields, each governed by its own rules and couplings. The word quantized means that these excitations occur in discrete units. The electromagnetic field can support a state containing one photon, two photons, or many photons. The electron field can support states containing electrons and positrons. These excitations may be spread through space, sharply concentrated or arranged in complicated superpositions, but the energy and other conserved properties are transferred in recognizable quantum units. To understand how an excitation can become concentrated in one region, it helps to think about waves with different wavelengths. A single perfectly regular wave extends indefinitely. Its peaks repeat across all space, so it has no sharply defined location. It does, however, possess a well-defined wavelength and therefore a well-defined momentum. A localized wave packet can be constructed by combining many waves with slightly different wavelengths, frequencies and momenta. Where those waves reinforce one another, they create a concentrated region of amplitude. Farther away, their peaks and troughs largely cancel. The result is a packet that occupies a limited region rather than extending with equal strength everywhere. This is not merely a mathematical trick. Wave packets provide a way to describe quantum excitations that are approximately localized. The localization can never be made completely perfect. To create a narrower packet, more wavelengths must be combined. Since wavelength is related to momentum, a tightly localized state requires a wider range of possible momenta. A state with one very precise momentum, by contrast, is associated with a broad wave extending through space. This relationship is expressed by Werner Heisenberg's uncertainty principle. In clear English, the relevant statement is that the uncertainty in position multiplied by the uncertainty in momentum cannot be made smaller than a limit determined by Planck's constant. The uncertainty principle does not merely describe a failure to measure carefully enough. It is not the claim that a particle follows one ordinary perfectly definite path while observers remain frustratingly unaware of it. The quantum state itself may not contain both an exact position and an exact momentum at the same time. A narrower range of possible positions requires a broader range of possible momenta. A narrower range of possible momenta requires a more extended position distribution. This gives quantum particles a character that is neither fully wave-like nor fully particle-like in the classical sense. Before detection, an excitation may be described by a quantum amplitude spread through a region. When it interacts with a detector, however, the result is local. A particle detector does not usually reveal a tiny object directly. Instead, it records what happens when the quantum excitation interacts with matter. A photon may be absorbed by an atom and raise one of its electrons to a higher energy state. A sufficiently energetic particle may ionize an atom, removing an electron. In a semiconductor detector, deposited energy can free electric charges that are then collected as a measurable current. These interactions occur in particular places. A detector may cover a broad region, while only one small part of it registers the event. The spatially extended quantum state does not leave a faint fraction of the particle in every possible detector element. One complete localized interaction is recorded. The probabilities for those possible locations are governed by the Born rule, named after Max Born. The Born rule connects a quantum amplitude to the likelihood of a measurement outcome. In simple terms, the probability of an outcome is determined by the squared magnitude of the corresponding quantum amplitude. A region with a larger amplitude is more likely to produce a detection. A region with no amplitude will not produce one. The rule predicts probabilities rather than one guaranteed individual result. Repeating the same experiment many times reveals a stable statistical pattern. This can be seen in the double-slit experiment. Individual photons or electrons are sent towards a barrier containing two narrow openings. Each particle produces one localized mark on the detector beyond the barrier. Yet after many events, the marks build into an interference pattern. The final pattern reflects the wave-like evolution of the quantum amplitude through the apparatus. Each individual mark reflects a discrete transfer of energy and momentum. The particle does not arrive as a faint mist spread across the detector. It arrives as one event. The precise meaning of this transition from a spread-out quantum state to a definite recorded result remains connected to the measurement problem. Different interpretations of quantum mechanics explain the process in different ways. Yet the observed pattern is clear. Quantum amplitudes evolve and interfere across space, while detectors register localized outcomes. The tracks seen in cloud chambers and bubble chambers can make particles look like tiny projectiles carving lines through matter. The reality is more subtle. A cloud chamber contains a supersaturated vapor. When a charged particle passes through, it ionizes atoms and molecules along its route. Droplets then form around those ions, creating a visible trail. A bubble chamber works through a related principle. It contains a superheated liquid, and charged particles trigger the formation of bubbles along regions where ionization occurs. The photographed line is therefore not a direct image of a naked particle. It is a sequence of many separate interactions between a quantum field excitation and the surrounding material. Each interaction leaves a small visible consequence. Together, those consequences allow physicists to reconstruct a path like history. The track may curve in a magnetic field, revealing the sign of the particle's charge and helping determine its momentum. It may split into several branches where an unstable particle decays. Other tracks may begin suddenly when new particles are created. These events reveal another important difference between quantum particles and classical objects. Particle number is often not permanently conserved. An unstable particle can disappear and produce several different particles. An electron and a positron can annihilate into photons. A sufficiently energetic collision can create particle and antiparticle pairs. What remains conserved are quantities such as total energy, momentum, electric charge, and angular momentum, along with other relevant quantum numbers. The fields remain present throughout the process. What changes is their state. One field may lose an excitation while another gains several. Energy and conserved properties pass through the couplings between fields. The particles appearing before and after an interaction need not be the same in number or type. This is why the field picture is so powerful. The fields provide the continuous physical framework extending through space and time. Their quantum states can spread, interfere, and evolve. Particles are the discrete excitations through which those fields exchange energy, momentum, charge, and spin. They are not merely tiny balls, and they are not merely ordinary waves. They are quantum events waiting within the possibilities of fields. The word vacuum usually suggests a place from which everything has been removed. A vacuum flask contains very little air. A laboratory vacuum chamber is designed to remove as many gas molecules as possible. In ordinary language, the closer a region comes to containing nothing, the better the vacuum becomes. Quantum field theory uses the word differently. The quantum vacuum is not the complete absence of matter, fields, laws, or physical structure. It is the lowest energy state available to a collection of quantum fields. No detectable particles need to be present. There may be no electrons passing through the region, no photons arriving at a detector, and no atoms drifting nearby. Yet the underlying fields remain. The electron field is still there. The electromagnetic field is still there. The quark fields, neutrino fields, and Higgs field are still part of the description. They are simply in their vacuum states. A classical field can sometimes be imagined as perfectly still. Every value is fixed, every disturbance has vanished, and nothing changes unless an external influence arrives. A quantum field cannot be made completely still in that classical sense. Quantum uncertainty places limits on how precisely certain properties of a field can be defined together. Each field mode behaves in some respects like a quantum oscillator, and even its lowest possible state retains a minimum amount of quantum energy. This minimum is called zero-point energy. It does not mean that ordinary particles are constantly being created from literal nothing, and then hurriedly returned before anyone notices. That familiar picture is dramatic, convenient, and often misleading. The vacuum is not a tiny factory floor crowded with classical objects briefly springing into existence. Instead, the vacuum state contains unavoidable quantum uncertainty and measurable correlations. Quantities associated with the fields do not generally possess perfectly fixed classical values at every point. These features are often described as vacuum fluctuations. The term fluctuation can sound as though the field is visibly trembling through time like a loose window in the wind. More precisely, it refers to the spread of possible measurement outcomes and to correlations predicted for field observables in the vacuum state. Two measurements made at different places may display related statistical behavior, even when the vacuum contains no real particles that could be detected independently. Popular explanations often say that virtual particles continually pop into and out of existence. Virtual particles are useful elements in certain calculation methods, especially perturbation theory. They appear inside Feynman diagrams as intermediate contributions linking the measurable initial and final states of an interaction. They are not free particles briefly hiding from experimental equipment. A real photon can travel through space and be detected. A virtual photon is an internal feature of a particular mathematical expansion. Its properties need not match those of a freely propagating detectable photon. Different mathematical methods can sometimes describe the same physical effect without referring to virtual particles in the same way. This is a good sign that virtual particles should not be treated as tiny literal objects flickering through empty space. The physical predictions remain real, even when the popular picture becomes less theatrical. One important example is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged conducting surfaces placed extremely close together would experience a measurable force. The presence of the surfaces changes the electromagnetic conditions in the region between them. Only certain field modes are compatible with the boundaries, while a different set of modes is available outside. The resulting difference produces a force between the surfaces. The effect becomes significant only at very small separations, typically measured in millionths or billionths of a meter. At everyday distances, it is far too weak to make two dinner plates drift romantically towards one another. The Casimir effect is often presented as direct proof of zero-point energy. That description can be useful, but it is not the only valid way to calculate the phenomenon. Equivalent treatments describe the force through quantum interactions between the electric charges within the conducting materials. The measurable force is not in doubt. The preferred interpretation of the calculation requires more care. Another important vacuum-related effect appears in the spectrum of hydrogen. According to an early relativistic description, two particular hydrogen energy levels should have possessed exactly the same energy. In 1947, Willis Lamb and Robert Rutherford measured a small difference between them. This difference became known as the Lamb shift. Quantum electrodynamics explained it through the interaction between the electron, the atomic nucleus, and the quantized electromagnetic field. The vacuum state alters the effective behavior of the charged particles by a tiny but measurable amount. The effect is small, but its agreement with theory became one of the important successes of quantum field theory. The vacuum also plays a role in spontaneous emission. An atom can enter an excited state when one of its electrons occupies a higher energy configuration. Eventually, the atom may release a photon and settle into a lower energy state. In a purely classical picture, it can be difficult to explain why a perfectly stable excited configuration should begin radiating at one particular moment. Quantum field theory describes spontaneous emission as an interaction between the excited atom and the quantized electromagnetic field, including its vacuum state. The atom does not simply become bored and release a photon for something to do. Its possible transitions are governed by the coupling between the atomic system and the electromagnetic field. The phrase empty space can also cause confusion on cosmic scales. The space between planets, stars and galaxies is extremely sparse compared with Earth's atmosphere, but it is not completely empty. Interstellar space contains thin gas, dust, cosmic rays, magnetic fields and electromagnetic radiation. Intergalactic space contains still lower densities of matter, along with radiation and gravitational structure. The cosmic microwave background passes through the universe as faint electromagnetic radiation left from the early stages of cosmic history. All of this exists in addition to the underlying quantum vacuum states. Vacuum energy becomes especially puzzling when gravity is considered. In general relativity, energy and momentum influence the curvature of spacetime. It therefore seems natural to ask whether the energy associated with quantum vacuum states should also gravitate. Straightforward estimates can produce values enormously larger than the energy density associated with the observed acceleration of cosmic expansion. This disagreement is called the cosmological constant problem, and it remains one of the deepest unresolved conflicts between quantum field theory and cosmology. Dark energy is the name given to whatever drives the observed accelerated expansion of the universe. A cosmological constant, represented by a constant energy density of empty space, is consistent with current observations. However, the Casimir effect, the Lamb shift, and other laboratory phenomena do not by themselves prove that quantum vacuum energy is the source of dark energy. They demonstrate that quantum fields possess physically meaningful vacuum structure. They do not settle how the absolute energy of that structure contributes to gravity on cosmic scales. Empty space in quantum field theory is therefore not ordinary nothingness. It contains no detectable particles in its lowest energy state, yet the fields remain. Their uncertainty, correlations, and interactions influence measurable events. The vacuum is quiet, but it is not featureless, and beneath what appears to be nothing, the invisible fields are still there. A field does more than exist quietly across space. It can interact with other fields. In quantum field theory, these interactions are described through couplings. A coupling determines how strongly one field responds to another, and which transformations are allowed between their excitations. An electron, for example, is an excitation of the electron field. Because the electron carries electric charge, it interacts with the electromagnetic field. That interaction can change the electron's momentum, alter its energy, or allow it to emit and absorb photons. This is the basic field-based meaning of a force. One field influences the behavior of another because the laws of the theory connect them. The quantum field theory of electrically charged particles in the electromagnetic field is called quantum electrodynamics. Its modern calculational form was developed during the 20th century through the work of Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Their approaches look different mathematically, but they produce the same physical predictions. Quantum electrodynamics became one of the most precisely tested theories in science. It describes how electrons, positrons, and other electrically charged particles interact with the electromagnetic field. It also explains how photons are emitted, absorbed, and scattered. A photon is a quantist excitation of the electromagnetic field. Visible light consists of photons, as do radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. These forms of radiation differ in frequency and energy, but they all belong to the same electromagnetic field. When an excited atom emits light, energy is transferred from the atom into the electromagnetic field as one or more photons. When a photon is absorbed, its energy and momentum are transferred into matter. This makes photons real, detectable particles. They can travel freely through space, strike a detector, and produce a localized signal. Physicists also often say that electromagnetic forces are produced through the exchange of photons. That statement is useful, but it must be handled carefully. It should not be imagined as two electrons throwing tiny luminous balls at one another, rather like an unusually disciplined game of catch. In quantum electrodynamics, the interaction between charged fields is represented mathematically through contributions involving the electromagnetic field. When calculations are organized using perturbation theory, those contributions can be drawn as Feynman diagrams. A Feynman diagram uses lines and meeting points to represent terms in a mathematical expansion. An electron line may enter, interact, and leave with a different momentum. A photon line may connect parts of the diagram. More complicated diagrams represent additional possible contributions to the same overall process. These diagrams are extraordinarily useful for organizing calculations. They are not literal photographs of what happens in hidden microscopic space. The lines do not necessarily show tiny objects traveling along precise paths. The meeting points are not confirmed miniature collisions occurring at exact hidden locations. A Feynman diagram represents one term contributing to a quantum amplitude. Many diagrams may need to be combined before the theory produces a measurable prediction. This distinction becomes especially important when discussing virtual photons. A real photon can propagate freely. It satisfies the normal relationship between energy and momentum for a massless particle, and it can be detected directly. A virtual photon appears as an internal element of a perturbative calculation. It cannot be isolated and detected as a free particle. Its mathematical properties need not match those of a real photon. Virtual photons are therefore not ordinary photons briefly breaking the rules while travelling unseen between charges. They are calculation-dependent features used to describe the interaction. The underlying physical fact is that the electron field is coupled to the electromagnetic field. That coupling produces the measurable attraction, repulsion, radiation, and scattering associated with electromagnetism. This one fundamental interaction accounts for an astonishing amount of ordinary experience. The attraction between negatively charged electrons and positively charged atomic nuclei holds atoms together. The arrangement of electrons around nuclei gives atoms their chemical behavior. When atoms share or exchange electrons, they form chemical bonds. Molecules, materials, and biological structures all depend on these electromagnetic interactions. Friction is also largely electromagnetic. When two surfaces slide against one another, their atoms do not behave like perfectly smooth solid blocks. The uneven distributions of electric charge interact, while microscopic structures catch, deform, and release. Energy organized as large-scale motion becomes internal motion, vibration, and heat. The contact force supporting a book on a table is electromagnetic as well. The atoms in the book do not sit directly on top of the atoms in the table, as hard miniature spheres touching edge to edge. Their electron clouds resist being pushed into the same states. Electromagnetic repulsion contributes to this resistance, while the Pauli exclusion principle prevents identical electrons from occupying the same quantum state. Together, these effects produce the familiar experience of solidity. Your hand does not pass through a table because the quantum fields associated with the matter in each object strongly resist the required overlap and rearrangement. The force you feel is not evidence that matter is made from perfectly rigid substance. It is the macroscopic result of electromagnetic field interactions and quantum statistics. Many apparently separate everyday forces are therefore different expressions of the same deeper physics. The tension in a rope, the springiness of a mattress, the pressure of a gas, the rigidity of a wall, and the friction beneath a shoe all emerge from electromagnetic interactions among atoms, combined with quantum rules governing electrons. At the fundamental level, physics recognizes four interactions. Electromagnetism is one. The strong interaction binds quarks and helps hold atomic nuclei together. The weak interaction allows certain particle transformations and radioactive decays. Gravity is the fourth. Gravity is not included in the standard model of particle physics. At large scales, it is described by Albert Einstein's general theory of relativity. General relativity does not treat gravity as an ordinary force transmitted through a quantum field in the same way as electromagnetism. It describes mass and energy as shaping the geometry of space-time, while objects follow paths through that curved geometry. A complete and experimentally confirmed quantum theory of gravity remains unknown. This is one reason the field description, powerful though it is not yet a final theory of nature. Even within the Standard Model, forces are not simply listed as unrelated mechanisms. Their structure is governed by symmetry. The allowed couplings between fields depend on transformation rules built into the theory. These symmetries determine which particles can interact, which properties must be conserved, and why particular force-carrying fields appear. What feels like a push, a pull, or a collision in everyday life is therefore the surface expression of a deeper arrangement. Fields are coupled, their excitations exchange energy and momentum, and the patterns of those exchanges are constrained by the hidden symmetries of nature. In everyday language, symmetry often means visual balance. A butterfly appears symmetrical because one wing resembles the other. A snowflake can be rotated and still look much the same. A circle remains unchanged no matter how it is turned around its center. In physics, symmetry has a broader and more precise meaning. A symmetry is a transformation that leaves the relevant physical laws or measurable predictions unchanged. The transformation might involve moving an experiment to another location, rotating it through space, shifting it to a different time, or changing part of its mathematical description. If the underlying laws remain the same, the system possesses a symmetry. This idea is far more powerful than a simple resemblance between two shapes. Symmetry constrains which equations are possible, which interactions may occur, and which physical quantities must remain conserved. One of the deepest connections between symmetry and conservation was discovered by the mathematician Emmy Noether. In 1918, Noether established a theorem showing that every continuous symmetry of a physical system is associated with a corresponding conservation law. A continuous symmetry is one that can be applied by any amount. An object can be rotated through a tiny angle or a large one. An experiment can be shifted forward in time by 1 second, 1 hour, or any interval in between. Noether's theorem revealed that familiar conservation laws are not merely separate rules added to physics. They arise from deep irregularities in the structure of nature. If the laws of physics do not change from one moment to another, the system possesses time translation symmetry. This symmetry is associated with conservation of energy. The phrase time translation does not mean travelling through time. It means that the same experiment performed tomorrow should obey the same fundamental laws as it does today. If the laws themselves quietly changed every Tuesday afternoon, energy conservation would become a much less reliable principle, and laboratories would require rather complicated calendars. The apparent uniformity of space leads to another connection. If an isolated experiment behaves according to the same laws after being moved from one location to another, the system possesses spatial translation symmetry. This symmetry is associated with conservation of momentum. The laws governing a collision do not depend on whether it occurs in London, on the Moon, or in a distant region between stars. Local conditions may differ, but the fundamental equations remain unchanged. Rotational symmetry means that the laws do not favour one absolute direction in space over another. An isolated experiment turned to face north, south, or any other direction should follow the same fundamental rules. This symmetry is associated with conservation of angular momentum. The connection is exact within the mathematical framework to which Noether's theorem applies. Conservation laws are therefore expressions of hidden symmetry. In quantum field theory, symmetry reaches even deeper. The possible fields and their interactions are strongly restricted by transformation rules. Physicists cannot simply add any convenient interaction to the Standard Model. The equations must respect the required symmetries, along with principles such as special relativity and quantum consistency. Some symmetries are called global. A global transformation is applied in the same way everywhere. For example, the mathematical phase of a quantum field may be changed by the same amount at every point in space-time, without altering observable predictions. A local transformation is allowed to vary from one place to another. That small change in wording has enormous consequences. If the phase of a charged matter field can be altered differently at every location, ordinary derivatives in the equations no longer behave consistently by themselves. An additional field is required to compensate for the local variation. In electromagnetism, that compensating structure is the electromagnetic gauge field. This leads to gauge symmetry. Gauge symmetry is sometimes described as an ordinary physical symmetry, but it is more carefully understood as a redundancy or invariance in the mathematical description. Different mathematical configurations can represent the same observable physical situation. Although this may sound like bookkeeping, the requirement of local gauge symmetry powerfully determines the form of the interactions. In the Standard Model, the electromagnetic weak and strong interactions are organized through gauge symmetries. Electromagnetism is associated with a comparatively simple gauge structure involving electric charge and the electromagnetic field. The weak interaction is associated with a more complicated gauge structure, connected to weak isospin and weak hypercharge. The strong interaction is associated with a gauge structure involving color charge and the gluon fields. These structures are often represented using compact mathematical group names, but the essential idea can be stated without symbols. Each gauge group describes a family of transformations under which the theory remains physically consistent. The corresponding gauge fields arise as the fields needed to preserve that local structure. Matter fields respond differently depending on the charges they carry. An electron carries electric charge, so it couples to the electromagnetic field. Quarks carry both electric charge and color charge, so they interact electromagnetically and through the strong interaction. Particles that possess weak isospin participate in the weak interaction. The word charge therefore has a wider meaning than positive or negative electricity. It describes a property determining how a field transforms and which gauge fields it can interact with. Electric charge is exactly conserved in all confirmed particle processes. A reaction may create charged particles or destroy them through annihilation, but the total electric charge before and after must remain equal. An electron and a positron can annihilate because their charges cancel. A lone electron cannot simply disappear into neutral photons, because that would violate charge conservation. Other proposed conservation rules are less exact. Physicists once treated electron number, muon number, and tau number as separately conserved quantities. Neutrino oscillations showed that neutrinos can change flavor as they travel, modifying this simple picture. The individual family numbers are therefore not exact conserved quantities in the straightforward way once imagined, although broader combinations may remain important within established theory. Not every symmetry is visible in the state of a physical system. Some are exact. Others are approximate and hold only within a limited range. A symmetry can also be hidden or spontaneously broken. Spontaneous symmetry breaking occurs when the underlying laws possess a symmetry, but the lowest energy state chosen by the system does not display it. The equations remain symmetrical, while the realized condition does not. This distinction becomes essential for understanding the Higgs field and the different behaviors of the electromagnetic and weak interactions. The Standard Model may appear at first to contain an untidy catalogue of electrons, quarks, neutrinos, photons, gluons, and other particles. Beneath that crowded surface lies a more compact organization. There are quantum fields. There are transformations under which their descriptions remain consistent. There are charges determining how those fields respond. And there are conservation laws emerging from the symmetries woven into the structure of the theory. What looks like a collection of unrelated particles is governed by a quiet architecture of hidden rules. The visible world is built largely from a family of quantum excitations called fermions. Electrons are fermions, quarks are fermions. Muons, tau particles, and neutrinos also belong to this broad category. Together their fields provide the matter content of the Standard Model. Fermions possess a quantum property called half-integer spin. Spin is a form of intrinsic angular momentum, but it should not be imagined as a tiny ball physically rotating around an axis. elementary particles have no confirmed solid surface that could spin in the ordinary mechanical sense. Instead, spin describes how a quantum state behaves under rotations and how it responds to magnetic fields and other interactions. Fermions have spin values such as 1/2. Bosons, by contrast, possess integer spin values. This difference produces dramatically different collective behaviour. The statistical rules governing fermions were developed through the work of Enrico Fermi and Paul Dirac. They are known as Fermi-Dirac statistics. Their most important consequence is closely connected to the Pauli exclusion principle, named after Wolfgang Pauli. The exclusion principle states that two identical fermions cannot occupy precisely the same quantum state at the same time. Electrons in an atom therefore cannot all settle into the lowest available state. Instead, they fill a layered arrangement of atomic orbitals. Each orbital can hold only a limited number of electrons with distinct quantum properties. This organization produces electron shells and helps explain the repeating structure of the periodic table. The chemical behavior of an element depends strongly on the arrangement of its outer electrons. Carbon forms its characteristic bonds because of its electron configuration. Noble gases are relatively unreactive because their outer electron shells are already filled. The exclusion principle therefore contributes not only to atomic stability, but also to chemistry, materials, and the structure of living organisms. It also helps explain why ordinary matter occupies space. When two solid objects are pushed together, the electrons within their atoms cannot simply collapse into identical states. Rearranging them into the same region requires placing some electrons into higher energy configurations. Electromagnetic repulsion between negatively charged electrons also resists the overlap. The apparent solidity of matter therefore emerges from both electromagnetic interaction and quantum statistics. A table feels solid not because it is filled with perfectly rigid miniature objects, but because its fermion fields and electromagnetic fields strongly resist the rearrangement required for another object to pass through it. The electron field extends throughout the universe. Every electron in every atom is an excitation of that same field. An electron in a laboratory is not merely similar to an electron inside a distant star. It is identical in mass, charge, and spin, because both are excitations of one underlying quantum field. Quarks follow the same general principle. There are 6 known quark flavors: up, down, strange, charm, bottom, and top. Up quarks and down quarks are the most important for ordinary matter. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. Strange, charm, bottom, and top quarks are heavier. They are usually produced only in energetic environments such as particle collisions, cosmic ray interactions, or the extremely hot conditions of the early universe. Most decay rapidly into lighter particles. The matter fields are arranged into 3 generations. The first generation contains up quarks, down quarks, electrons and electron neutrinos. The second contains charm quarks, strange quarks, muons and muon neutrinos. The third contains top quarks, bottom quarks, tau particles and tau neutrinos. Each generation follows a broadly similar pattern, but the particles become heavier in the later generations. Why nature contains exactly 3 generations remains unknown. Ordinary visible matter depends overwhelmingly on the first generation. Atoms require electrons, while atomic nuclei are built from protons and neutrons containing up and down quarks. Electron neutrinos are produced in processes including nuclear reactions and radioactive decay, although they rarely interact with matter. Neutrinos were once thought to be massless. Experiments later showed that they can change from one flavor into another while traveling. This phenomenon is called neutrino oscillation. Takaaki Kajita helped establish oscillations among neutrinos produced in Earth's atmosphere, while Arthur MacDonald and the Sudbury Neutrino Observatory demonstrated that neutrinos arriving from the Sun were changing flavor rather than simply disappearing. Neutrino oscillation requires differences between neutrino masses, showing that at least some neutrinos possess non-zero mass. This result revealed that the simplest original form of the Standard Model was incomplete. The origin of neutrino mass remains an active area of research. The masses of fermions are connected in part to their interactions with the Higgs field. However, it would be misleading to say that the Higgs field creates all the mass of ordinary matter. The direct masses of up and down quarks contribute only a small fraction of the mass of a proton or neutron. Most of that mass arises from the energy associated with the strong interaction inside them, including the motion of quarks and the activity of gluon fields. Since protons and neutrons account for most of the mass of atoms, much of the weight of ordinary matter comes from confined quantum field energy. Fermion fields provide the excitations that form matter, but they do not act alone. Electromagnetic gauge fields govern interactions involving electric charge. Gluon fields bind quarks through the strong interaction. Weak gauge fields allow particle transformations and radioactive processes. Matter is therefore not a passive collection of fermions. It is a changing system of fermionic excitations continually shaped, bound and transformed by bosonic fields. Fermion fields provide the particles that make up matter, but matter would remain inert and disconnected without another broad family of quantum fields. These are bosonic fields. Their excitations are called bosons, and unlike fermions, bosons are not restricted by the Pauli exclusion principle. Large numbers of identical bosons can occupy the same quantum state at the same time. This difference begins with spin. Bosons possess integer values of intrinsic spin, such as 0 or 1. As with fermions, spin should not be pictured as a tiny object literally rotating. It is a quantum property that determines how a particle state behaves under rotations and how collections of identical particles are organized. The statistical behavior of bosons was developed through the work of Satyendranath Bose and Albert Einstein. In the early 1920s, Bose found a new way to count the possible states of particles of light. Einstein extended the method to particles with mass. The resulting rules became known as Bose-Einstein statistics. Because bosons can gather into the same state, they can produce collective effects that would be impossible for fermions. Laser light is one familiar example. In a laser, many photons are produced with closely matched frequencies, phases, and directions. The photons occupy highly coordinated quantum states, creating light that is coherent and strongly concentrated. A less familiar example is a Bose-Einstein condensate. When certain atoms are cooled to temperatures extremely close to absolute zero, a large fraction can settle into the same lowest energy quantum state. Their individual wave-like descriptions overlap, and the atoms begin to behave collectively as one extended quantum system. Although the atoms themselves contain fermions, the complete atoms can behave as bosons when their total spin is an integer. The first gaseous Bose-Einstein condensates were produced in laboratories during the 1990s, revealing quantum behavior on a scale large enough to be studied directly. Within the standard model, several bosonic fields are responsible for the fundamental interactions. The photon is the gauge boson of electromagnetism. Photons are excitations of the electromagnetic field. They carry electromagnetic radiation, including visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. Photons have no electric charge and no rest mass. Because they are massless, electromagnetic influences can extend over very large distances. Their strength weakens as they spread through space, but there is no fixed range beyond which electromagnetism abruptly stops operating. The weak interaction is carried by three different gauge bosons. These are the positively charged W boson, the negatively charged W boson, and the electrically neutral Z boson. The weak interaction allows particles to change identity. It is involved in beta decay, in which a neutron can transform into a proton while producing an electron and an antineutrino. At the field level, one of the neutron's down quarks changes into an up quark through the weak interaction. Weak bosons also govern many neutrino interactions. Neutrinos do not respond to electromagnetism because they carry no electric charge, but they do participate in the weak interaction. The unified description of electromagnetism and the weak interaction is called electroweak theory. Sheldon Glashow, Abdus Salam and Stephen Weinberg were central to its development. Electroweak theory showed that the electromagnetic and weak interactions arise from a shared underlying gauge structure. Their very different appearances at low energies result from the way that symmetry is hidden through the Higgs field. Photons remain massless, while the W and Z bosons acquire substantial masses through their interaction with the Higgs field. The W bosons have masses of roughly 80 billion electron volts, while the Z boson has a mass of about 91 billion electron volts. These large masses make the weak interaction extremely short-ranged. A virtual weak boson cannot mediate an interaction effectively across ordinary atomic distances. The weak interaction acts mainly across distances smaller than roughly 1/10,000th of the diameter of a proton. Its range is tiny, but its effects are essential. The weak interaction powers parts of the nuclear reaction chain inside stars, contributes to radioactive decay, and allows neutrinos to interact with matter. The strong interaction is carried by gluons. Gluons are the gauge bosons of quantum chromodynamics, the quantum field theory of quarks, and the strong interaction. The Standard Model contains 8 gluon states. This number arises from the mathematical structure of color charge. Quarks carry color charge, while antiquarks carry corresponding anticolor charge. The names red, green and blue are used for the 3 color charges, but they have no connection to visible color. Gluons are themselves electrically neutral, yet they carry combinations of color and anticolor charge. This makes them profoundly different from photons. Photons do not carry electric charge, so in ordinary quantum electrodynamics they do not directly interact with one another. Gluons carry the very type of charge to which they respond. As a result, gluon fields interact with other gluon fields. This self-interaction gives the strong force its unusual behavior. At extremely short distances, quarks can behave almost as though they are free. As the separation increases, however, the strong field does not simply fade away in the same manner as the electromagnetic field. Energy accumulates in the gluon field between the quarks. Eventually it becomes energetically favorable to create new quark and antiquark excitations, rather than isolate the original quarks. This behavior contributes to confinement. Quarks and gluons are therefore not observed as isolated free particles under ordinary conditions. They remain bound inside color-neutral composite particles such as protons, neutrons and mesons. The force carriers of the Standard Model are all gauge bosons. The photon carries electromagnetism. The W and Z bosons carry the weak interaction. Gluons carry the strong interaction. Gravity does not yet fit into the same experimentally confirmed framework. A hypothetical quantum particle of gravity is called the graviton. If it exists in the simplest expected form, the graviton would be a massless boson with spin 2. It would represent a quantum excitation of a gravitational field. No graviton has been directly detected. Gravitational waves have been observed, but detecting those classical waves does not amount to detecting individual gravitons. The energy carried by one graviton in a typical observable gravitational wave would be extraordinarily small, making direct detection extremely difficult. Not every boson is a force-carrying gauge boson. The Higgs boson is also a boson, but it belongs to a different category. It is an excitation of the Higgs field, which is a scalar field. A scalar field has spin 0 and assigns a magnitude rather than a spatial direction to every point. The Higgs boson does not mediate one of the Standard Model gauge forces in the way photons, weak bosons and gluons do. Instead, the Higgs field alters the vacuum structure of electroweak theory and contributes to the masses of elementary particles. Bosonic fields therefore perform several roles. They transmit radiation, they carry interactions, they allow particles to decay and transform, they bind quarks into protons and neutrons, they help organize the masses of elementary particles. Matter may be formed from fermionic excitations, but its behavior is shaped by bosonic fields. Through them, atoms bind, stars shine, nuclei change, and light crosses the universe. They provide the interaction structure through which the apparently solid world remains constantly connected. Inside every proton lies one of the most energetic and counterintuitive regions in ordinary matter. A proton is often introduced as a small positively charged particle, sitting quietly inside an atomic nucleus. That description is useful, but it can make the proton sound like a simple solid bead. In reality, a proton is a highly dynamic quantum system. Its internal behavior is described by quantum chromodynamics, the quantum field theory of quarks, gluons, and the strong interaction. The word chromodynamics refers to color charge. Color charge has nothing to do with visible color. Quarks and gluons are far smaller than anything that could possess a familiar shade, and no microscopic red, green, or blue light is hidden inside a proton. The names red, green, and blue are labels for three forms of strong interaction charge. Antiquarks carry corresponding anti-color charges, conventionally called anti-red, anti-green, and anti-blue. These labels help describe how quark and gluon fields transform and interact. They are mathematical properties, much as positive and negative are labels for electric charge. Observable particles must be color neutral. This means their color charges combine into a state with no overall color. A proton contains a combination conventionally described as one red quark, one green quark, and one blue quark, although the individual assignments are not permanently attached to particular quarks. Gluon interactions continually exchange color charge, so the internal arrangement is constantly changing. The complete three-color combination is neutral. Particles made from three quarks are called baryons. Protons and neutrons are the most familiar baryons. A proton has two up valence quarks and one down valence quark. A neutron has one up valence quark and two down valence quarks. Particles made from a quark and an antiquark are called mesons. In a meson, a color and its corresponding anticolor combine to form a color-neutral state. The idea of quarks emerged during the 1960s. Murray Gell-Mann and George Zweig independently proposed that the growing collection of known particles could be organized using more fundamental constituents. Gell-Mann called them quarks, while Zweig initially used the term aces. At first, many physicists treated quarks mainly as a useful classification device. No isolated quark had been detected, and the idea that protons and neutrons contained smaller point-like constituents remained uncertain. Important evidence arrived through deep inelastic scattering experiments at the Stanford Linear Accelerator Center. In these experiments, high-energy electrons were directed into protons. Lower-energy scattering tends to probe the proton as a whole. At much higher energies, however, the electron can reveal smaller structures inside it, rather as shorter wavelength light can resolve finer details. The scattering pattern suggested that the proton contained compact point-like constituents. These constituents were initially called partons. They were later identified with quarks and gluons. The experiment showed that a proton was not a featureless sphere. It contained internal components carrying fractions of its momentum and electric charge. Yet the strong interaction behaves very differently from electromagnetism. Electric forces usually weaken as charged particles move farther apart. Quarks do not simply drift free when separated. One reason is a property called asymptotic freedom. David Gross, Frank Wilczek, and David Politzer established that the strong interaction becomes weaker when quarks are examined at extremely short distances or very high energies. Under those conditions, quarks can behave almost as though they're free. This explains why the point-like constituents inside a rapidly struck proton can appear relatively independent during the brief instant of a high-energy collision. At larger distances, the behavior reverses. The strong interaction becomes more intense. This leads to confinement, the principle that isolated quarks and gluons are not observed as freely travelling particles under ordinary conditions. Imagine trying to pull two quarks apart. The energy stored in the gluon field between them rises as their separation increases. Instead of weakening and allowing the quarks to escape, the field can form a narrow region of concentrated energy, often compared to a stretched tube. Eventually enough energy accumulates to create a new quark and antiquark pair. The original quarks do not emerge alone. They combine with the newly produced excitations to form colour-neutral particles. This is why high-energy collisions produce jets of hadrons rather than isolated quarks. A hadron is a composite particle built from quarks and gluons. Baryons and mesons are both hadrons. When an energetic quark is produced in a collider, it begins a cascade of radiation and particle formation. The resulting hadrons travel in roughly the same direction, creating a narrow spray known as a jet. Physicists study these jets to infer the behaviour of quarks and gluons that cannot be observed independently. The interior of a proton is therefore much more complicated than three quiet quarks occupying fixed positions. The two up quarks and one down quark are called valence quarks, because they determine the proton's overall quantum numbers, including its electric charge. But the proton also contains gluon fields carrying a large share of its momentum. The energy of those gluon fields can temporarily produce quark and antiquark excitations. These fluctuating contributions are often called the sea of quarks and antiquarks. A proton is better understood as a changing quantum state of interacting quark and gluon fields. Its internal components move at speeds close to the speed of light. Gluons are continually emitted, absorbed and interacting with one another. Quark and antiquark contributions appear within the quantum state and disappear again through field interactions. This activity is responsible for most of the proton's mass. A proton has a mass corresponding to roughly 938 million electron volts. The bare masses of its two up valence quarks and one down valence quark account for only a small fraction of that total. Most of the mass arises from the energy of the strong interaction, including the motion of quarks, the energy stored in gluon fields, and the complex dynamics of confinement. This is a direct expression of mass-energy equivalence. The proton's mass is not simply the sum of three tiny ingredient masses. It reflects the total energy of a confined quantum system. Calculating that system is extremely difficult because the strong interaction becomes intense at proton-sized distances. Ordinary perturbative methods, which treat interactions as small corrections, no longer work reliably. One major alternative is lattice quantum chromodynamics. In lattice quantum chromodynamics, physicists represent spacetime as a discrete grid for the purpose of numerical calculation. Quark fields occupy points on the grid, while gluon-related quantities connect to neighbouring points. Powerful computers then simulate the possible field configurations and calculate properties such as hadron masses. The lattice is a computational method, not evidence that spacetime itself is physically made from tiny cubes. These calculations have reproduced the masses of protons, neutrons and other hadrons with impressive accuracy, supporting the quantum chromodynamic description. The proton inside an ordinary atom is therefore not a small lump of static substance. It is a confined storm of quark and gluon fields. Most of its mass comes from their motion and interaction. Its stability arises from a balance governed by quantum chromodynamics. Its internal colour activity remains hidden because only colour-neutral combinations can appear freely. The familiar solidity of matter depends on these invisible processes. Every table, stone, planet and human body contains vast numbers of protons and neutrons. Within each one, strong quantum fields remain active. What looks calm and solid from the outside is sustained by extraordinary energy moving through an unseen world within. The Standard Model describes the electromagnetic and weak interactions as two expressions of a deeper electroweak theory. At very high energies, these interactions are united through a shared gauge structure. Yet at ordinary energies they appear strikingly different. Electromagnetism reaches across enormous distances. Its force carrier, the photon, has no rest mass. The weak interaction acts across distances far smaller than the width of a proton. Its carriers, the W bosons and the Z boson, are extremely massive by particle standards. This difference created a serious theoretical problem. The gauge symmetry underlying electroweak theory naturally describes massless gauge bosons. Adding mass directly to the W and Z fields would disrupt the symmetry and damage the mathematical consistency that made the theory work. Yet experiments clearly showed that the weak interaction had a very short range, strongly suggesting that its carriers must be massive. Physics needed a mechanism that could preserve the deeper symmetry of the laws while allowing the observable particles to behave as though that symmetry had been hidden. The solution involves spontaneous symmetry breaking. The phrase sounds dramatic, but the central idea can be illustrated gently. Imagine a perfectly round bowl with a small ball resting somewhere inside it. If the lowest point lies directly at the centre, the ball settles there, and the final arrangement preserves the bowl's rotational symmetry. Now imagine a different surface shaped like a circular valley surrounding a raised centre. Every direction around the valley is equivalent. The underlying shape is perfectly symmetrical. Yet when the ball settles, it must choose one particular position somewhere around the ring. The laws remain symmetrical, but the chosen lowest energy state does not display the full symmetry. This is spontaneous symmetry breaking. Nothing outside the system needs to push the ball towards a preferred direction. The structure of the lowest energy states allows many equivalent choices, and the system settles into one of them. During the 1960s, several physicists developed versions of a mechanism that applied this idea to quantum fields. The contributors included Peter Higgs, François Englert, Robert Brute, Gerald Guralnick, Carl Richard Hagen, and Tom Kibble. Their work showed how a field filling the vacuum could hide an underlying gauge symmetry, while allowing certain particles to acquire mass. That field became known as the Higgs field. The Higgs field is a scalar quantum field. A scalar field assigns a magnitude to every point in space and time without requiring a direction. Temperature is a familiar classical example of a scalar quantity. A room can have a temperature at each location, but that temperature does not point north, south, up, or down. The Higgs field is not a temperature field, but it shares this directionless mathematical character. Its most unusual property is that its lowest energy state does not correspond to a field value of 0. Even in the vacuum, where no Higgs particles are present, the Higgs field possesses a non-zero value throughout space. This is called the Higgs vacuum expectation value. The field does not need to be excited into visible particles to influence other quantum fields. Its background vacuum value is already present everywhere. As the electroweak universe cooled after its extremely hot early stages, the Higgs field settled into this non-zero state. That altered the behavior of the electroweak gauge fields. Before symmetry breaking, the underlying theory treats the relevant gauge fields in a unified way. After the Higgs field takes on its non-zero vacuum value, combinations of those fields behave differently. One combination remains massless and becomes the electromagnetic field. Its quantum excitation is the photon. Other combinations acquire mass and become the W bosons and the Z boson. The photon remains massless because the electromagnetic part of the symmetry remains unbroken. The weak bosons become massive because their fields interact with the non-zero Higgs background in a way that changes the structure of their equations. This does not mean that the Higgs field slows the W and Z bosons through friction. A common analogy compares the Higgs field to a crowded room in which a famous person attracts a cluster of people and therefore moves less easily. The image can suggest why stronger interaction might be associated with greater inertia, but it also creates problems. Particles are not being dragged through a sticky, cosmic substance. They do not lose energy merely by moving through the Higgs field. A particle travelling at constant velocity in empty space does not experience resistance from it. Instead, inertial mass emerges from the mathematical structure of the field equations once the Higgs field has a non-zero vacuum value. Mass determines how a particle's energy relates to its momentum and how strongly it resists acceleration. The interaction with the Higgs field changes that relationship. Elementary fermions also acquire mass through their couplings to the Higgs field. These couplings are called Yukawa interactions, named after the physicist Hideki Yukawa, although the Higgs-related Yukawa couplings are distinct from Yukawa's original proposal for the nuclear force. Electrons, quarks, muons and tau particles each couple to the Higgs field with different strengths. The stronger the coupling, the larger the resulting elementary particle mass. The electron couples relatively weakly and is light. The top quark couples far more strongly and is the heaviest known elementary particle. The Standard Model does not explain why the Yukawa couplings possess their particular values. It includes them as quantities measured through experiment. Why one fermion couples weakly, while another couples strongly remains one of the unanswered questions hidden beneath the theory's success. Neutrino masses introduce an additional complication. The simplest original Standard Model treated neutrinos as massless. Their observed oscillations show that they possess non-zero masses, but the precise mechanism producing those masses has not yet been established. They may involve extremely weak Higgs couplings, additional neutrino fields, or a mechanism beyond the simplest Standard Model. The Higgs field itself can also be excited. A detectable quantum excitation of the field is called the Higgs boson. Just as a photon is an excitation of the electromagnetic field, the Higgs boson is an excitation around the Higgs field's non-zero vacuum value. Producing one requires concentrating an enormous amount of energy into a tiny region. The search took place at the European Organisation for Nuclear Research, widely known by the name CERN, near Geneva on the border between Switzerland and France. CERN operates the Large Hadron Collider, a circular particle accelerator roughly 27 kilometers in circumference. Inside it, proton beams travel in opposite directions at speeds extremely close to the speed of light. Powerful magnets guide the beams around the ring before the protons collide at selected points. Most collisions produce familiar combinations of particles. Very occasionally, enough energy is concentrated in the correct way to produce a Higgs boson. The Higgs boson is highly unstable and survives for only an extraordinarily brief interval before decaying into other particles. It cannot be observed directly as a long-lived object. Physicists reconstruct its presence statistically from the energies, momenta and identities of its decay products. Two large experiments, the Atlas collaboration and the CMS collaboration, searched independently for these decay patterns. In July 2012, both collaborations announced the discovery of a new boson with a mass near 125 billion electron volts. Later measurements showed that its spin, decay behavior and interaction strengths were consistent with the Higgs boson predicted by the Standard Model. The discovery confirmed that a Higgs-like field is part of nature. It did not mean that physicists had found the source of all mass. The Higgs field contributes to the elementary masses of quarks, charged leptons and the W and Z bosons. But most of the mass of ordinary visible matter lies in protons and neutrons. The bare masses of the quarks inside them account for only a small part of their total mass. Most proton and neutron mass arises from the energy of quark motion, gluon fields and strong interaction confinement. The Higgs field gives the quarks their elementary masses, but quantum chromodynamics generates most of the mass contained in atomic nuclei. The measured Higgs mass also opened deeper questions. Calculations suggest that the stability of the Higgs vacuum depends delicately on the measured masses of the Higgs boson and the top quark. Current values place the universe near a boundary between absolute stability and a possible long-lived metastable state. If the vacuum is metastable, it could in principle decay into a lower energy state, although any expected lifetime would be vastly longer than the current age of the universe. The Higgs mass also contributes to the naturalness problem. Quantum corrections tend to pull the Higgs mass towards very high energy scales, unless some deeper principle, New symmetry or additional physics stabilizes it. Proposals include supersymmetry, composite Higgs models and other extensions of the Standard Model, but none has yet received decisive experimental confirmation. The Higgs field therefore solves one profound problem while pointing towards several others. It explains how electroweak symmetry can remain present in the laws while hidden in the vacuum. It allows the weak bosons and elementary fermions to possess mass without destroying the gauge structure of the theory. And throughout apparently empty space, its non-zero value quietly remains. The invisible field is not dragging matter through the universe. It is helping define what matter means by mass. Entanglement is often introduced through a pair of particles. Two photons may be produced together, travel in opposite directions, and later display correlations that cannot be explained by treating each one as an entirely independent object with its own pre-written set of properties. Yet entanglement is not a special thread that occasionally appears between tiny particles. It is a general property of quantum states. Atoms can become entangled. Photons can become entangled. Larger laboratory systems can become entangled. Most importantly here, the states of quantum fields can also contain entanglement. A quantum state is entangled when the complete state cannot be separated into independent states for its individual parts. Imagine two quantum systems called 1 and 2. In an unentangled state, the condition of system 1 can be described separately from the condition of system 2. Each possesses its own quantum state, and the combined description is simply those two states placed together. In an entangled state, that separation is impossible. Only the complete joint state is fully defined. The individual parts may not possess separate definite quantum properties before measurement, even though measurements performed on them display precise correlations. This is much stranger than placing a left glove in one box and a right glove in another. With the gloves, each box contains a definite object from the beginning. Opening one box merely reveals what was already there and allows the contents of the distant box to be inferred. Quantum entanglement can produce correlations that cannot be explained by assuming that each system carried an ordinary hidden instruction list specifying every possible result in advance. This problem became famous in 1935 through an argument developed by Albert Einstein, Boris Podolsky, and Nathan Rosen. The Einstein-Podolsky-Rosen argument considered two systems that had interacted and then separated. Quantum mechanics described them with one shared state, allowing measurements on one system to be strongly correlated with measurements on the other. Einstein, Podolsky, and Rosen argue that if one could predict a distant measurement result without disturbing the distant system, then the corresponding property ought to represent an element of physical reality. They believed quantum mechanics might therefore be incomplete. Perhaps the particles really did possess definite properties all along, hidden beneath the quantum description. Einstein was particularly uncomfortable with the apparent tension between entanglement and locality. He did not accept that a measurement performed in one place should physically change a distant reality instantaneously. The question remained largely philosophical until John Bell transformed it into an experimentally testable problem. In 1964, Bell proved a theorem showing that no theory based on local hidden variables can reproduce every statistical prediction of quantum mechanics. Local means that influences do not travel faster than light between separated regions. Hidden variables means that the systems possess underlying definite properties determining the outcomes, even when those properties are not included in the ordinary quantum state. Bell derived limits on the strength of correlations that any such local, hidden variable theory could produce. These limits became known as Bell inequalities. Quantum mechanics predicts that carefully prepared entangled systems can violate them. Experiments can therefore distinguish between the predictions of quantum theory and the entire broad class of local hidden variable explanations. John Clauser and his colleagues performed an influential Bell test during the 1970s using entangled photons. Alain Aspect later conducted more refined experiments during the early 1980s, changing measurement settings rapidly enough to strengthen the separation between the two sides of the experiment. Anton Zeilinger and many other researchers extended these methods across increasing distances and with greater control over possible experimental loopholes. Modern Bell tests have repeatedly violated Bell inequalities in agreement with quantum predictions. The results tell us that nature cannot be explained by a model in which separated systems carry ordinary local hidden instructions sufficient to determine every measurement outcome. They do not show that usable information travels faster than light. The outcome obtained on either side of a Bell experiment appears individually random. An observer cannot choose the result and use it to encode a message. Only when the two sets of results are later brought together through ordinary communication do the correlations become visible. That comparison cannot occur faster than light. Entanglement, therefore, challenges local classical explanations without providing an instantaneous communication service. The universe remains mysterious, but it has not kindly included free faster-than-light broadband. Within quantum field theory, entanglement is even more fundamental than the familiar picture of two particles flying apart. A quantum field extends across space, and its state can contain correlations between different regions. Consider dividing space into two areas. The field degrees of freedom associated with one region may be entangled with those associated with the other. This can remain true even when the field is in its vacuum state. The quantum vacuum is therefore not a collection of perfectly independent points, each quietly minding its own business. It contains correlations across space. Measurements of field quantities in different regions can display related statistical behavior, because those regions belong to one shared quantum state. These vacuum correlations do not require ordinary particles to travel between the points at the moment of measurement. They are part of the structure of the field state itself. When particles are discussed as entangled, the underlying description can often be expressed in terms of quantum fields. The entanglement may exist between field excitations, between different field modes, or between properties such as momentum, spin, and polarization. Two photons can be entangled in polarization. Two electrons can be entangled in spin. A single field excitation may even be entangled across different spatial regions or possible modes. This does not mean that the particles are connected by a hidden physical cord. It means that the full quantum state cannot be decomposed into separate independent descriptions of the parts. Entanglement also plays a major role in decoherence. A quantum system is rarely perfectly isolated. It interacts with surrounding air molecules, photons, thermal radiation, and the microscopic degrees of freedom within measuring devices. Through these interactions, the system becomes entangled with its environment. Information about the system's possible states spreads into an enormous number of environmental degrees of freedom. The different alternatives then become extremely difficult to recombine and observe as an interference pattern. This process is called decoherence. Decoherence helps explain why large objects appear to occupy stable classical states rather than obvious superpositions. It does not require a conscious observer. A dust grain can become entangled with scattered light whether or not anyone is watching. A detector can record an event and become correlated with it long before a human sees the result. Consciousness is not known to create entanglement, collapse field states, or hold the universe together through attentive staring. The physical interaction is enough. Field entanglement now connects several major areas of theoretical research. In black hole physics, it is central to discussions of Hawking radiation and the black hole information problem. Quantum fields inside and outside a horizon can possess entangled correlations, raising difficult questions about how information is preserved as a black hole evaporates. In quantum information science, entanglement is treated as a physical resource for tasks including quantum teleportation, quantum cryptography, and some forms of quantum computation. The word teleportation can sound more dramatic than the process itself. Quantum teleportation transfers an unknown quantum state using shared entanglement and ordinary classical communication. It does not transport matter instantaneously, and no person disappears in one laboratory before arriving neatly dressed in another. Some researchers have also explored whether patterns of entanglement might be deeply connected to the emergence of space-time geometry. Ideas involving holography, tensor networks, and quantum gravity suggest that space-time relationships may be linked to how quantum information is organized. These proposals are important and mathematically rich, but they are not yet experimentally established as a final account of space-time. The grounded conclusion remains striking enough. Quantum fields are not merely separate values assigned independently to every location. Their states can possess correlations that stretch across space and cannot be reduced to independent local pieces. What appears divided may still belong to one inseparable quantum description. Entanglement is therefore not an unusual extra added to the field picture. It is one of the ways quantum fields reveal that reality cannot always be understood by breaking it completely separate parts. Quantum field theory became extraordinarily successful, but its early calculations often produced a rather alarming result: infinity. Physicists tried to calculate the energy of an electron, the strength of its electric charge, or the probability of an interaction, and the mathematics sometimes returned quantities without any finite limit. This was not a small numerical disagreement. An infinite particle mass or an infinite probability is not something a laboratory can quietly round down. The difficulty arose partly from the nature of fields. A field can be analysed as a collection of modes with different wavelengths and frequencies. Shorter wavelengths correspond to higher momenta and higher energies. In a continuous theory, there is no obvious smallest wavelength. The calculation may therefore include contributions from modes that become shorter and more energetic without limit. Quantum interactions add further complexity. An electron does not behave as though it were completely isolated from the electromagnetic field. Its measured properties include the influence of that interaction. When physicists calculate a process using perturbation theory, they begin with a simpler approximation and then add increasingly complicated corrections. The first approximation might show an electron emitting and absorbing one virtual photon. A more detailed correction may involve additional virtual photons, temporary electron and positron contributions, and many other allowed intermediate arrangements. Each possibility contributes to the final quantum amplitude, naively summing over every possible momentum carried by these internal contributions can produce divergent expressions. Very high energy, extremely short distance behavior may contribute without bound. The problem became especially serious during the early development of quantum electrodynamics. The theory clearly contained the correct physical ideas. It explained interactions between electrons, positrons, and photons, yet its calculations seemed contaminated by infinities. A controlled first step is called regularization. Regularization temporarily modifies the calculations so that the divergent quantities become manageable. One method might impose a maximum energy or a minimum wavelength. Another may treat space-time as though it possesses a slightly different number of dimensions. Other methods alter the mathematical form of the integrals while preserving the important symmetries of the theory. The regularizing device is not usually claimed to be a literal feature of nature. It acts more like a carefully labelled support structure. It allows the problematic expression to be examined without pretending that the infinity has already disappeared. Renormalization then connects the theoretical parameters in the calculation to quantities that can actually be measured. The theory may begin with a parameter representing the electron's underlying mass or electric charge before the full effects of quantum interactions are included. These are sometimes called bare parameters. They are not directly observable. The measured electron mass already includes the electron's interaction with the electromagnetic field. The measured electric charge likewise includes the influence of surrounding quantum field effects. Renormalization rewrites the theory in terms of these physical, measured quantities at a chosen energy scale. The divergent pieces are absorbed into the relationship between the bare parameters and the observable ones. The resulting predictions for measurable differences and interaction probabilities can then remain finite. This procedure is not simply a careless subtraction of one infinity from another. a successful renormalization scheme follows precise rules. It must preserve the symmetries of the theory, produce consistent predictions, and allow the same measured inputs to determine many independent outcomes. If the method were merely hiding mistakes, it would not repeatedly predict new measurements with extraordinary accuracy. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed different methods for calculating quantum electrodynamic processes. Freeman Dyson later demonstrated that these formulations were mathematically related and could be understood within one common perturbative framework. This helped establish quantum electrodynamics as a coherent theory rather than a collection of separate calculational tricks. Its predictive success became astonishing. One famous example is the magnetic moment of the electron. A simple, relativistic quantum description predicts a particular relationship between the electron's spin and its magnetic behavior. Quantum field interactions produce a tiny additional correction known as the anomalous magnetic moment. Calculating that correction requires contributions from increasingly complicated virtual processes. Experimental measurements and quantum electrodynamic calculations agree to many decimal places, making the result one of the most precise agreements between theory and experiment in science. Renormalization, therefore, did not merely rescue a theory from embarrassing infinities, it allowed the theory to make some of the most exact predictions ever tested. A deeper interpretation emerged through the renormalization group. The renormalization group is not an ordinary group of researchers, despite the name sounding rather like a committee assigned to tidy up theoretical physics. It is a mathematical framework describing how the parameters of a theory change when the scale of observation changes. Kenneth Wilson played a central role in developing this modern understanding during the 20th century. The key idea is that physics depends on scale. A coastline looks jagged when examined closely and smooth when viewed from far away. A material may appear continuous at human scales while revealing atoms at much shorter distances. Quantum fields also behave differently depending on the energy or distance at which they are probed. Coupling constants, which describe the strengths of interactions, can run with energy. A running coupling constant is not literally moving. Its effective measured value changes with the scale of the experiment. In quantum electrodynamics, the vacuum surrounding an electric charge contains quantum polarization effects. Virtual contributions from charged fields partially screen the charge when it is viewed from farther away. At shorter distances, less of this screening lies between the observer and the charge, so the effective electromagnetic coupling becomes slightly stronger. This behavior is called vacuum polarization. The strong interaction runs in the opposite and far more dramatic direction. At high energies and short distances, the strong coupling becomes weaker. This is asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Politzer. At larger distances, the strong coupling grows, contributing to the confinement of quarks and gluons. The interaction strengths are therefore not fixed numbers entirely independent of context. They are linked to the scale at which the fields are examined. This scale-dependent view leads naturally to effective field theory. An effective field theory is designed to describe phenomena accurately within a particular range of energies or distances. It does not need to remain valid at every imaginable scale. At low energies, the details of extremely heavy particles or very short distance structures may have only small effects. Those details can be summarized through a limited set of additional terms rather than described explicitly. Newtonian gravity is highly effective for planets and spacecraft, even though general relativity provides a deeper description. Fluid mechanics works beautifully without tracking every molecule. In the same way, a quantum field theory can make extremely accurate predictions within its tested domain while remaining incomplete at far higher energies. The Standard Model itself may be an effective field theory. It works extraordinarily well across the energies so far explored, yet it may eventually be replaced or extended by a deeper framework involving new particles, new symmetries, or quantum gravity. This perspective transformed renormalization. What had first looked like a desperate attempt to remove infinities became a lesson about how nature is organized across scale. Low-energy physics does not always require complete knowledge of the smallest possible distances. The influence of unknown high-energy structures can often be contained within a small number of measurable parameters. Renormalization reveals how descriptions change as the viewpoint changes. It shows why the same fields can appear weak at one scale and strong at another, why measured particles already include the effects of their interactions, and why an incomplete theory can still be astonishingly precise. The infinities did not disappear because physicists learned to ignore them. They became manageable because physicists learned to ask which quantities are truly observable and at what scale the question is being asked. Quantum fields cannot be seen directly. No microscope has photographed the electron field stretching through a laboratory, and no detector has captured an image of the Higgs field quietly filling empty space. Yet quantum fields are not accepted because they provide an elegant story, or because their mathematics happens to be beautiful. They are accepted because calculations built from them repeatedly predict measurable outcomes with extraordinary accuracy. The fields reveal themselves through what they cause. One of the most important ways to study them is through scattering experiments. In a scattering experiment, physicists prepare incoming particles with known energies and a momenta, direct them towards a target or towards one another, and measure what emerges. The outgoing particles may travel in different directions. They may possess different energies. Entirely new particle types may appear. By comparing these results with quantum field calculations, physicists can infer which fields interacted, how strongly they were coupled, and what conservation laws govern the process. The basic principle resembles learning about an unseen object by throwing something towards it and examining what comes back. The comparison is useful, although particle scattering is considerably more precise and usually involves fewer tennis balls. To reach the necessary energies, physicists use particle accelerators. A particle accelerator uses electric fields to increase the energy of charged particles. Magnetic fields then guide, focus, and bend the resulting beams. Some accelerators direct particles into a fixed target. Others circulate two beams in opposite directions and bring them into collision. Higher collision energies allow experiments to probe shorter distances and produce heavier field excitations. The Large Hadron Collider at the European Organisation for Nuclear Research, commonly called CERN, is the most powerful particle collider yet constructed. It accelerates protons around a circular tunnel roughly 27 kilometers in circumference. The protons travel at speeds extremely close to the speed of light and collide with combined energies measured in trillions of electron volts. A proton is itself a composite state containing quarks, antiquark contributions, and gluons. During a collision, it is usually individual constituents within the two protons that interact most directly. The concentrated energy can briefly produce excitations that do not normally exist in ordinary matter. Heavy quarks, weak bosons, Higgs bosons, and other unstable particles may appear for tiny fractions of a second before decaying. Several major experiments study these collisions. ATLAS and CMS are general-purpose detectors designed to investigate a broad range of particle processes. Both played central roles in discovering the Higgs boson. ALICE specializes in heavy ion collisions, where lead nuclei are brought together at enormous energies. These collisions create a short-lived state called quark-gluon plasma, resembling the hot dense matter believed to have filled the early universe. LHCb focuses especially on particles containing bottom quarks. It studies subtle differences between matter and antimatter and searches for rare decays that might reveal physics beyond the standard model. These detectors do not usually photograph unstable particles directly. A Higgs boson, top quark, or W boson decays far too rapidly to leave a long visible trail. Instead, physicists measure the particles produced by the decay. Their energies, directions, electric charges and identities are reconstructed from signals deposited in layers of detector material. Conservation laws then help researchers work backwards. Total energy and momentum must balance. Electric charge must remain conserved. Particular decay patterns must match the known properties of the proposed parent particle. A new particle therefore appears as a repeated excess of events with a characteristic combination of decay products. The challenge is that ordinary known processes can sometimes produce similar signatures. These expected events are called background. Researchers use detailed theoretical calculations, detector simulations, and control measurements to estimate how much background should appear. They then ask how unlikely the observed excess would be if no new particle existed. This is where statistical significance becomes essential. Particle physicists generally require extremely strong evidence before announcing a discovery. A commonly used threshold corresponds to a probability of roughly 1 chance in several million that the signal arose from a background fluctuation alone. Even then, independent confirmation and continuing measurement remain important. Quantum fields are also tested through precision experiments, rather than only through enormous collisions. The magnetic properties of electrons provide one of the clearest examples. Quantum electrodynamics predicts a tiny difference between the simplest value expected for an electron's magnetic moment and the value produced after quantum field interactions are included. This anomalous magnetic moment has been measured and calculated to extraordinary precision. The close agreement between theory and experiment, extending across many decimal places, is among the strongest quantitative successes in physics. The muon has an analogous, anomalous magnetic moment. Because a muon is more than 200 times heavier than an electron, its magnetic behavior is more sensitive to contributions from heavier fields and particles. The Fermi National Accelerator Laboratory in the United States has performed precise measurements of the muon's magnetic moment. Comparing these measurements with standard model predictions remains an active and technically difficult area. The experimental results are highly precise, but the theoretical calculation includes complicated contributions from strong interaction physics. Some methods and datasets have produced tension between theory and experiment, while newer calculations have changed the scale and interpretation of that disagreement. The situation remains unsettled rather than serving as a confirmed discovery of new physics. The weak interaction has been tested in many other ways. Beta decay reveals how quarks transform through the weak field. Neutrino scattering tests the couplings of neutrinos to W and Z bosons. Electron-positron colliders have provided especially clean measurements because electrons and positrons are elementary particles rather than composite objects like protons. The Large Electron-Positron Collider, formerly operated at CERN in the tunnel, now used by the Large Hadron Collider, produced enormous numbers of Z bosons and measured their properties with high precision. The Stanford Linear Collider in California also investigated electroweak interactions through controlled electron and positron collisions. Together, these experiments tested the predictions of electroweak theory, including the masses, decay patterns, and interaction strengths of the weak bosons. Quantum chromodynamics is tested through different signatures. High-energy collisions produce particle jets that reveal the presence of quarks and gluons. The number, direction, and internal structure of these jets can be compared with calculations of strong field radiation and hadron formation. Deep inelastic scattering shows how momentum is distributed among the quarks and gluons inside protons. Measurements made at different energies reveal scaling behavior and the running of the strong coupling, confirming that the interaction weakens at short distances through asymptotic freedom. Not all evidence for quantum fields requires a giant accelerator. Atomic spectroscopy measures the precise frequencies of light absorbed and emitted by atoms. Small shifts in atomic energy levels reveal interactions with a quantized electromagnetic field. The Lamb shift, first measured by Willis Lamb and Robert Rutherford, showed a difference between hydrogen levels that simpler theories predicted should coincide. Quantum electrodynamics explained the shift. The Casimir effect provides another lower energy example. Closely spaced conducting surfaces experience a small force connected to the quantum behavior of the electromagnetic field under boundary conditions. No single experiment proves that quantum fields are literally the final substances of reality. Experiments test predictions, not philosophical labels. It remains possible that quantum fields emerge from a deeper framework not yet known. What makes quantum field theory so persuasive is the network of evidence. The same framework explains atomic spectra, particle decay, scattering probabilities, magnetic moments, weak interactions, strong interaction jets, and the production of the Higgs boson. These results span enormous differences in energy and experimental design. Again and again, the invisible fields predict what visible instruments will record. Their presence is not established by one dramatic observation. It is revealed by the quiet consistency of thousands of measurements, all pointing towards the same hidden structure beneath matter. Quantum fields extend far beyond laboratories and particle accelerators. The same fields that govern electrons, photons, and quarks also operate within planets, stars, galaxies, black holes, and the evolving universe. Electromagnetic fields fill cosmic environments. Earth's magnetic field creates a magnetosphere that guides charged particles arriving from the Sun. Similar fields shape stellar atmospheres, influence solar flares and direct cosmic rays through interstellar space. Quantum electrodynamics underlies the way stars emit and absorb light. Atoms and ions interact with photons at specific energies, producing characteristic spectral lines. By studying those lines, astronomers can identify hydrogen, helium, iron, and many other elements in stars thousands or millions of light years away. Quantum fields also help stars produce their energy. Inside the Sun, positively charged nuclei repel one another through electromagnetism. Quantum tunneling allows some nuclei to cross that barrier and approach closely enough for the strong interaction to bind them. The weak interaction is equally important. During the proton-proton chain, one proton is transformed into a neutron, allowing hydrogen to begin fusing into helium. Without quantum tunneling, weak interactions, and strong interaction binding, ordinary stars could not shine as they do. At the end of some stellar lives, gravity compresses matter into neutron stars. A neutron star may contain roughly the mass of the Sun within a sphere only about 20 kilometers wide. Matter reaches densities comparable to those inside atomic nuclei. Quantum statistics help resist further collapse. Neutrons are fermions, so the Pauli exclusion principle prevents them from all occupying the same quantum state. Nuclear field theory and general relativity are also required to describe the star's structure. Around black holes, quantum fields behave in even stranger ways. During the 1970s, Stephen Hawking showed that quantum fields in curved spacetime predict thermal radiation associated with a black hole's event horizon. This became known as Hawking radiation. It is often pictured as a pair of virtual particles appearing near the horizon, with one falling inward and the other escaping. That image can serve as a rough mnemonic, but the real calculation concerns quantum field modes and how different observers define particles in curved space-time. A related prediction is the Unruh effect, associated with William Unruh. An inertial observer can describe a field as being in its vacuum state, while an accelerating observer describes that same state as a thermal environment. The temperature would be tiny under ordinary conditions, but the principle reveals that particle descriptions can depend on motion. The expanding universe introduces similar effects. As spacetime changes, quantum field modes evolve. A state that appears empty at one time may later contain particles according to another natural description. Quantum fields may therefore have played a central role in the earlier stages of cosmic history. One influential proposal is cosmic inflation, a brief period of extremely rapid expansion. Alan Guth, Andrei Linde, and Alexei Starobinsky were among the major contributors to inflationary theory. In many models, inflation is driven by the energy of a quantum field. Small quantum fluctuations in early universe fields would then have been stretched to enormous scales. Slightly denser regions later attracted more matter through gravity, eventually growing into galaxies and galaxy clusters. Evidence for primordial variations appears in the cosmic microwave background. The Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft mapped tiny temperature differences across this ancient radiation. Those variations are roughly 1 part in 100,000 and possess statistical features broadly consistent with primordial quantum fluctuations. The evidence strongly supports the existence of early density variations, but it does not reveal the identity of the field that may have driven inflation. No confirmed inflaton particle has been detected, and alternative early universe models remain under study. Even so, the connection is remarkable. The same quantum field principles used to describe particle collisions and atomic transitions may also explain the original irregularities from which the large-scale structure of the observable universe emerged. From magnetospheres and starlight to neutron stars, black holes and galaxies, the invisible fields remain present. They do not merely fill the universe, they may have helped shape it. Quantum field theory has become one of the most successful frameworks in science. Within the Standard Model, it describes electrons, quarks, neutrinos, photons, gluons, weak bosons, and the Higgs boson. It explains electromagnetism, the weak interaction, and the strong interaction with extraordinary precision. Yet the Standard Model is not a complete explanation of nature. It contains many measured parameters, including particle masses and coupling strengths, whose values are not derived from a deeper accepted principle. The electron has one mass, the muon another, and the tau particle is heavier again. The differences span enormous ranges, but the theory does not explain why. The same mystery appears in the 3 generations of matter. Each generation follows a similar pattern, yet only the first is needed to build ordinary atoms. Why the other 2 exist remains unknown. Neutrinos reveal another limitation. The simplest original Standard Model treated them as massless, but neutrino oscillations show that they possess non-zero masses. Their origin therefore requires an extension to the original theory. Dark matter presents a larger gap. Its gravitational influence appears in the motions of stars within galaxies, the behavior of galaxy clusters, gravitational lensing, and the large-scale structure of the universe. Yet no confirmed Standard Model particle has the right properties to explain all of it. Dark energy is even more mysterious. It is the name given to the phenomenon associated with the accelerating expansion of the universe. It is not a confirmed quantum field with known particles and measured microscopic behavior. The cosmological constant provides a simple description of that acceleration, but quantum field theory creates a severe problem. Straightforward estimates of vacuum contributions can exceed the observed value by an enormous number of orders of magnitude. This is the cosmological constant problem, and it remains unresolved. The Higgs field creates another difficulty known as the hierarchy problem. The Higgs mass is far below the highest proposed fundamental energy scales. Quantum corrections appear capable of pushing it much higher, unless some deeper mechanism protects it, or produces very precise cancellations. Supersymmetry is one proposed solution. It links fermions and bosons through a new symmetry and introduces partner particles that could cancel some large quantum corrections. It may also provide dark matter candidates. No supersymmetric particle has been confirmed. Grand unified theories pursue a different possibility. They attempt to combine the strong, weak, and electromagnetic interactions within one larger symmetry. Such theories may explain relationships among particle charges and could predict effects such as proton decay. So far, no confirmed proton decay has been observed. Gravity remains the clearest missing part. Albert Einstein's general theory of relativity described gravity remarkably well as the curvature of space-time. It explains planetary motion, black holes, gravitational lensing, and gravitational waves. But when general relativity is treated as a fundamental quantum field theory at all energies, the calculations produce divergences that cannot be controlled using the same finite renormalization methods that work for the Standard Model. At energies far below the Planck scale, gravity can still be treated successfully as an effective quantum field theory. The real difficulty appears under extreme conditions, such as the earliest universe or the deepest regions associated with black holes. A complete theory of quantum gravity remains unknown. String theory proposes that elementary particles arise from tiny vibrating strings and naturally includes a quantum state with the expected properties of a graviton. Loop quantum gravity instead attempts to quantize space-time geometry itself, suggesting that areas and volumes may possess discrete structure. Both are major research programs. Neither has received decisive experimental confirmation. Other approaches explore holography, causal sets, emergent space-time and quantum information. These ideas raise a final question. Are quantum fields truly fundamental, or are they effective descriptions of something deeper involving strings, geometry, entanglement, or principles not yet discovered? Physics does not know. That uncertainty does not weaken what quantum field theory has already achieved. Where it has been tested, it predicts nature with astonishing accuracy. Its limits do not erase its successes. They simply mark the places where the invisible reality beneath everything may itself rest upon something deeper. Quantum fields are the invisible reality beneath everything, because modern particle physics describes matter and interaction as excitations and couplings of fields extending throughout space. The path towards this picture began with Newtonian forces, moved through Michael Faraday's classical fields and James-class Maxwell's electromagnetism, then changed again through Max Planck's quantization, Albert Einstein's relativity and Paul Dirac's relativistic theory of the electron. Electrons, photons, quarks, gluons, weak bosons, and the Higgs boson are not treated as unrelated miniature objects, each as an excitation of a corresponding quantum field. Even the quantum vacuum is not absolute nothingness. It is the lowest energy state of those fields. Their couplings produce electromagnetic weak and strong interactions. Gauge symmetries and conservation laws constrain how those interactions unfold. Fermion fields provide matter, bosonic fields mediate interactions, and the Higgs field contributes to elementary particle mass. Most of the mass inside protons and neutrons, however, comes from strong field dynamics, atomic spectra, the Lamb shift, magnetic moment measurements, scattering experiments, particle colliders, neutrino observations, and the discovery of the Higgs boson all support this framework. Quantum field theory still does not fully explain gravity, dark matter, dark energy, neutrino mass, or the deepest structure of space-time. Its incompleteness does not diminish its success. Apparently solid reality rests upon fields that cannot be seen directly, yet continuously shape every atom, ray of light, chemical bond, living body, planet, and distant star.